So you write a Lambda function. You click deploy, you test it, and it takes 1.2 seconds. Cool. You push it to production, but suddenly, half your users are complaining about 2-second delays, while the other half, they're getting lightning-fast 100-millisecond responses. Welcome to this explainer. I'm your host, and today we're going to solve a mystery that plagues developers everywhere, a mystery that causes serious frustration, downtime, and honestly, costs businesses serious money.
Now, to understand why this inconsistent latency happens, we've got to strip away the magic and look exactly at what is going on under the hood when AWS Lambda runs. Today, we'll be covering 1. The serverless illusion, 2. The execution environment, 3. The database connection trap, 4. Surviving flash sales, 5. Hidden traps and retries, and we'll wrap it all up with 3 rapid takeaways.
All right, let's jump right into section 1. The serverless illusion. Just keep in mind as we go that your serverless compute code doesn't just float around in the ether, it actually needs a completely isolated box to run in. AWS Lambda is serverless compute. You hand AWS a zip file or a container image and they run it. But without that secure isolation we just mentioned, your code would clash with someone else's workloads. Which brings us to our core question. Why are half your users experiencing 2-second delays? Because you wrote the code, but you don't actually know what happens when Lambda runs. Let me show you what is actually going on. We need to think of Lambda not as some magic server in the sky, but as a temporary factory workspace. When a request comes in, Lambda has to build a workspace just for you. AWS calls this the execution environment, and this brilliantly illustrates our first major point. It is a secure, temporary factory workspace built by Lambda to run your code without clashing with other workloads. Okay, let's dive into this. Section 2, the execution environment. We're going to map out the exact step-by-step mechanical flow of how this works. When your function receives its very first request, it enters the init phase. This is that notorious cold start. First, Lambda downloads your code. Then, it bootstraps your chosen runtime like Node.js or Python. Next, it runs your static initialization code. Now, this is absolutely critical. Static initialization is all the code you wrote outside of your main handler function. It imports libraries and sets up database connections. Then and only then, it enters the invoke phase. This is where your actual handler code executes to process the event. But here's the kicker. When it finishes, Lambda doesn't just destroy the environment, it freezes it.
Think about that. It's like a chef opening a brand new restaurant just to cook you one single burger. That is the init phase, and it takes time. But if a second customer walks in right after you, well, the kitchen is already open, the grill is hot, the chef just cooks the burger. That's the invoke phase on a warm start. Lambda bypasses the init phase entirely and jumps straight into your handler. Moving on to section 3, the database connection trap. I want you to pay very close attention to this next part, because this is what causes massive application failure. Here is where people fail.
Notice the stark contrast in architectural approach here. If you put your database connection logic inside the handler, every single time that handler runs, it opens a brand new connection. It completely crushes your database, and it slows down the function execution. To implement this correctly as an AWS developer, you must pull that database connection object outside the handler method. When Lambda reuses that frozen execution environment for a warm start, those objects outside the handler remain initialized. You just write a tiny bit of logic inside the handler to check if the connection already exists before creating a new one. Literally, this one single change drastically reduces your latency.
So what happens when the stakes get incredibly high? Let's talk about section 4, surviving flash sales. Imagine a sudden, massive traffic spike to your API that you absolutely have to handle flawlessly. Let's say you have a flash sale, and exactly 5,000 users hit your API at exactly the same second. Even with highly optimized code, Lambda has to spin up 5,000 brand new execution environments in parallel. That is 5,000 cold starts. If your business cannot afford that latency and you simply cannot lose those sales, you have to architect a solution. And the solution? You execute on a feature called provisioned concurrency. The crucial point here is that you explicitly configure Lambda to pre-initialize a set number of execution environments. Lambda runs that init phase ahead of time. So when those 5,000 users hit your API, the environments are red hot and ready to respond instantly. No cold start delay. They are ready to go.
All right, let's look at some very specific edge cases in section 5, hidden traps and retries.
For anyone taking the DVA-02 exam or, just managing production infrastructure, you must know these scenarios. How does Lambda handle errors during execution? Well, if your code times out or crashes during the invoke phase, Lambda completely resets the execution environment. But here is the trick. It does not clear the local/temp directory. Every execution environment gives you up to 10 gigabytes of scratch space in /temp. And because that directory content persists between warm invocations, a subsequent request reusing that environment can easily access leftover files. You must always account for that in your code by checking if the cache has the data you need or clearing sensitive data out completely. Also, you really need to understand the invocation retry trap. If you invoke Lambda directly and synchronously, like from an API gateway, and it fails, Lambda does not automatically retry. You just get an error back. But if you trigger it asynchronously, like dropping a message into an SNS topic, Lambda will automatically retry the failed invocation up to 2 times. Section 6, let's lock this down. 3 rapid takeaways. 1. The execution environment lifecycle has an init phase for setup and an invoke phase for execution. 2. Static variables outside the handler and files in the /tmp directory persist across warm starts. 3. You mitigate cold starts by moving heavy initialization code outside the handler or by paying for provisioned concurrency. And I'll leave you with one final warning. Never assume your execution environment will live forever. AWS terminates these environments every few hours for routine maintenance, even if they are constantly being invoked, so your application code must be fundamentally stateless. Keep that rule in mind for your next build, and you will never be caught off guard by the Lambda lifecycle again. Which leaves me with one final question for you to go check after this explainer. Are you absolutely sure your current Lambda functions aren't secretly holding on to state right now? Picture this. You connect an SQS to your Lambda function. You drop 10,000 messages in. Everything seems fine until suddenly your function starts crashing. But here's the kicker. Those messages, they keep reappearing in the queue. They're getting processed again and again and again. You have just created an infinite loop of death, and it is literally costing you a fortune in AWS compute fees. So, why did 10,000 messages create an infinite loop of death? Well, the harsh truth is, it's because you treated a queue trigger the exact same way you treat an API gateway trigger. You didn't understand how AWS actually invokes your code. Let me show you what is actually going on under the hood. Lambda is entirely passive. Seriously, it's just a dead piece of code sitting on a server somewhere doing absolutely nothing until an event source tells it to wake up and execute. But how that event actually reaches your code, that changes everything about how your function scales, how it fails, and exactly how you have to write it. Okay, let's dive into our agenda for this explainer. We're going to cover Section 1, the infinite death loop. Section 2, push, sync versus async. Section 3, the pull model. Section 4, the batch failure trap. Section 5, kinesis pipeline paralysis. And finally, Section 6, the golden retry rules. There are only 2 fundamental ways AWS services communicate with Lambda, push or pull. Section 1, the infinite death loop. Like I said, it basically comes down to this. Either a service throws an event directly at your function, or Lambda actively reaches out and grabs the data itself. Section 2, push, sync versus async. Let's break down the push model first because it's incredibly common. This actually splits into 2 very distinct types, synchronous and asynchronous. Let's start with synchronous push. In this scenario, a service, like API Gateway, calls your Lambda function and waits. It literally holds the connection open. Your function runs, processes the data, and hands the response directly back to the caller. But what if your code crashes? API Gateway gets a 502 bad gateway error. And here's the crucial part. Lambda does not retry the execution. It just failed. That's it. You have to write the retry logic yourself right there in the client application. Now, compare that to asynchronous push. Think of services like Amazon S3 or SNS. When a file drops into an S3 bucket, S3 doesn't have the time to sit around waiting for your function to process some massive video file. Instead, it takes the event, hands it over to an internal Lambda queue, receives a 202 accepted response immediately, and just walks away. Think about that for a second. The service that triggered the function is already gone before your code even starts running. So who handles the errors? Lambda does. If your asynchronous function crashes, Lambda will automatically put the event back in that internal queue and retry it up to 2 more times, with delays in between. Section 3, the pull model.
But here is where we leave the push model completely behind. What happens when you have a massive stream of data coming from Kinesis, or thousands of messages just sitting in an SQS queue? Well, those services do not push data to Lambda. Instead, you have to configure what's called an event source mapping.
An event source mapping is a dedicated resource managed entirely by the Lambda service. Think of it as an army of invisible background pollers. These pollers are constantly reaching out to your SQS queue or your DynamoDB stream asking, hey, do you have any data? If the answer is yes, the poller grabs a batch of records, say 10 messages at once, bundles them all up into a single JSON payload, and pushes that entire batch into your Lambda function synchronously.
Let's use a restaurant analogy to make this crystal clear. Synchronous push is like a customer at the drive-thru. They wait right there at the window until you hand them their food. Asynchronous push? That's a delivery driver dropping a box of supplies on your loading dock and immediately driving away. If you happen to drop the box, your manager automatically orders a replacement. But an event source mapping, that is you actually walking into the freezer, grabbing a batch of 10 burger patties, bringing them over to the grill, and cooking them all at once. Think about that for a second.
Section 4. The batch failure trap. Now, here is exactly where people mess up. This is where the costly failures happen. Developers will write their code to process that batch of 10 SQS messages. Messages 1 through 9, they process perfectly. But message 10 throws a database error, and the entire function crashes. So, what happens to those first 9 successful messages? Well, because the function failed, the event source mapping assumes the entire batch failed. It takes all 10 messages and puts them right back onto the SQS queue. A few seconds later, Lambda pulls the queue again, grabs those exact same 10 messages, and processes them all over again. You are now duplicating database writes, and you are paying for compute power that you absolutely do not need.
So how do we fix it? To implement this correctly as an AWS developer, you must configure your event source mapping to report batch item failures. You write your code to catch that specific error on message 10, and you return only the ID of that specific failed message back to the Lambda service. When you do that, Lambda will delete the 9 successful messages from the queue, and it will only retry the one single message that actually failed. It is a total game changer. Section 5. Kinesis pipeline paralysis. Now, imagine this scenario. You have a highly critical, strictly ordered data stream coming from Amazon Kinesis. If a batch of records fails here, the event source mapping will retry that same batch over and over and over again. And because Kinesis is strictly ordered, Lambda is going to block that entire shard. It literally will not read any new data until that failing batch either finally succeeds or the data completely expires days later. This will completely paralyze your pipeline, just absolute downtime. Section 6. The golden retry rules. Listen, this is the ultimate exam trap and a classic real-world gotcha. You absolutely must know how AWS handles retries. Let's break it down. API gateway, 0 automatic retries. SNS or S3, exactly 2 automatic retries. SQS or Kinesis, it retries the batch indefinitely until the data expires or until you are smart enough to send it to a dead letter queue. Let's lock this down with 3 rapid takeaways for this explainer. Number 1, synchronous invocations force the client application to handle errors, while asynchronous invocations are automatically retried by Lambda twice. Number 2, event source mappings use a pull model where Lambda actively pulls your streams and queues to process data in batches. And number 3, you absolutely must handle partial batch failures in your code when using event source mappings to prevent those infinite retry loops and duplicate processing. I want to leave you with one final warning. Never, and I mean never, attach an event source mapping to a queue without configuring a dead letter queue. Without it, a single bad message will poison your entire system, it'll consume all your concurrency, and it will quietly drain your AWS budget. So I want you to look at your architecture today. Are your Lambda triggers secretly set up to fail gracefully, or are they just one bad message away from an infinite loop? Demystifying the limits of AWS Lambda concurrency. Imagine this. Your app just went completely viral. 10,000 users click buy at the exact same second. And you're feeling pretty good because you chose AWS Lambda and you were told it scales infinitely, right? Wrong. Instead of processing those 10,000 orders, your API gateway starts throwing out 502 errors. Your logs are literally screaming too many requests exception at you, and your entire AWS account just completely locked up. So why did it break? Well, because Lambda doesn't actually scale infinitely. It hits a brick wall, and it just stops. let's dive into exactly why AWS Lambda suddenly stopped scaling, and more importantly, how you actually manage this in a real production environment.
Section 1. Understanding Lambda concurrency.
To understand why it breaks, we first have to understand how it grows. In Lambda, one request equals one execution environment. So if one user hits your API, Lambda spins up one environment. If 100 users hit it at the exact same time, Lambda automatically scales horizontally and spins up 100 environments in parallel. This right here is called concurrency. Concurrency is simply the number of in-flight requests your function is handling simultaneously. But here's the catch. AWS doesn't let you grow forever. By default, your entire AWS account has a strict concurrency limit of exactly 1,000 simultaneous executions per region. Think about that for a second. All of your functions share the exact same pool of 1,000 unreserved concurrent executions. If your marketing team runs a massive ad campaign and your checkout function suddenly scales up to use all 1,000 of those executions, it completely drains the pool. So when your completely unrelated password reset function gets triggered, there's absolutely no concurrency left. Lambda just throttles it. A viral spike in one part of your app just caused a massive outage in another. Section 2. The reserved concurrency trap. Now, here is where people mess up. They try to fix this shared pool problem by using a feature called reserved concurrency, and they completely misunderstand how it works. Let's say you configured 200 units of reserved concurrency on your checkout function. You probably think you're guaranteeing that it'll always have enough power, right? But reserved concurrency is a double-edged sword. It's not just a guarantee, it is a strict ceiling. By setting reserved concurrency to 200, you've isolated that function from the shared pool. If request 201 comes in, it gets throttled immediately. It literally doesn't matter if your account has 800 unused executions sitting totally idle. Your function is strictly blocked from using them. As a smart AWS developer, you actually use reserved concurrency strategically as a kill switch. You apply it to prevent a function from scaling totally out of control and overwhelming a fragile downstream resource, like a legacy relational database. You cap the Lambda so you don't crush the database.
Section 3. The provisioned concurrency fix.
Now, if what you actually care about is raw performance and eliminating cold starts during a massive traffic burst, you use provisioned concurrency. Instead of just reserving a slice of the pie, provisioned concurrency pre-initializes the execution environments, so they're red hot and ready to instantly process code. And here is the massive difference to remember. If a function uses up all of its provisioned concurrency, it does not throttle. It simply spills over into the standard unreserved pool and scales up like a normal function, dealing with cold starts but, crucially, keeping your app online.
Section 4. Event source scaling limits.
Imagine this scenario. You aren't using API Gateway. Instead, you're processing a massive data stream from Amazon Kinesis. You've got 10,000 records hitting the stream every single second. But you look at your Lambda metrics, and you notice your function is stuck at a concurrency of exactly 5. It refuses to scale any higher, and your data processing is falling completely behind. Why did horizontal scaling just stop? Well, because with stream-based event sources like Kinesis, Lambda scaling is entirely bottlenecked by the number of shards in your stream. Lambda will only spin up one concurrent execution per shard. If your Kinesis stream only has 5 shards, your Lambda concurrency is permanently capped at 5, no matter how many millions of records are waiting. To scale Lambda here, you actually have to split the Kinesis shards.
The exact same trap exists with Amazon SQS. You see, Lambda uses a fleet of invisible pollers to grab messages from your queue. It can scale up to add 1,000 concurrent executions per minute for SQS. But if you set a low reserved concurrency on that function, say 50, those SQS pullers are still going to grab a massive batch of messages and try to invoke your function. Lambda sees you hit your cap of 50, throttles the request, and drops the messages. So the messages go back to the queue, the pullers grab them again, and you've just created an endless cycle of throttling and retries.
Section 5. 3 rapid takeaways.
Let's lock this down. 1. Concurrency is the number of simultaneous executions, and by default, all functions in your region share a hard limit of 1,000. 2. Reserved concurrency guarantees capacity, but it acts as a strict maximum cap. Provisioned concurrency, on the other hand, pre-warms environments but actually allows spillover scaling. And 3. Lambda scaling is dictated by the event source. Kinesis caps concurrency at the shard level, while SQS scales dynamically, but can absolutely cause throttle loops if combined with strict reserved limits.
I'll leave you with one final warning.
Never assume throttling is just a Lambda problem. Always check what is triggering the function, because the way you configure the event source maps directly to how AWS allows your compute to scale.
So, picture this. You just deployed a brand new microservice, right? And you share the endpoint with a client.
Well, barely 10 minutes later, a botnet scrapes your URL. It starts spamming 100,000 requests a second, and it just absolutely crushes your backend database.
And worse, it racks up a $5,000 AWS bill. Yeah, that hurts. Let that sink in. So why did this happen? It's because you left the front door wide open. But don't worry, let me show you how to actually protect your systems. Amazon API Gateway is that front door. It sits right there between the dangerous, unpredictable internet and your fragile backend servers. Look, if you don't use it, your backend code has to handle everything itself. We're talking routing, SSL termination, rate limiting, and authenticating users. Your actual business logic just drowns in networking code. But API Gateway, it rips all of that out and handles it at the very edge of the AWS network. Think of API Gateway like the bouncer and the receptionist at a highly exclusive club. The club is your back end. A client walks up to the door, and API Gateway intercepts them before they ever even get a glimpse of the inside.
Now, let's break down exactly how the HTTP request flows through the system. It goes through 4 distinct steps. Step 1 is the method request. Remember our analogy? This is the bouncer. When an HTTP request hits your route, say a GET request to /users, the method request checks if it's actually formatted correctly. Are the query string parameters valid? Did they include the right headers? And more importantly, who are you? This is exactly where you configure authorizers. You can attach Amazon Cognito to validate a user token, you can use IAM policies, or even trigger a custom Lambda authorizer to check your own database. If the client fails here, API Gateway just throws a 401 unauthorized or a 403 forbidden error. And the best part? The backend never even knows they were there. Moving on to step 2, the integration request. Okay, so you pass the bouncer. Now you meet the receptionist. The receptionist takes your messy, real-world HTTP request and translates it into exactly what the backend expects. For example, if your backend requires a very specific JSON format, you use what's called a mapping template right here. This transforms the incoming data on the fly so your backend doesn't have to.
Then we get to step 3. This is where the backend actually does its job. It processes the data and hands a response right back to the receptionist. Which brings us to step 4, the integration response and method response. Here, API Gateway catches that raw backend data, uses another mapping template to format it into a clean JSON response, attaches the correct HTTP status code, and finally, hands it back to the client.
Think about that for a second. Your backend compute didn't parse any headers. It didn't check user tokens. It didn't have to format JSON. It just received clean data, processed it, and went to sleep. That, my friends, is the true power of a managed API gateway.
But here's where people fail, and I see this all the time. They build this beautiful API, and then they hard-code their backend URLs directly into their integration settings. So what happens? When they need to test a new version of their app, they have to rewrite and redeploy the entire API just to point to a test server. It's a mess. To implement this correctly as an AWS developer, you need to use stages and stage variables.
So what are they? Well, a stage is just a named reference to a snapshot of your API. You create a dev stage, a test stage, and a prod stage. Now, instead of hard-coding that backend URL, you use a stage variable. When a request hits the dev stage URL, API Gateway dynamically injects the development database endpoint. When it hits the prod stage URL, it injects the production endpoint. You maintain one single API definition, and it's dynamically routed based entirely on the environment.
Now, I want you to imagine this. You just launched a massive marketing campaign. Traffic spikes by 5,000%. Your backend simply cannot handle it, and it begins to fail. If you don't configure throttling on your API Gateway stages, your system dies. But if you do, API Gateway instantly steps in to save the day. It allows you to set a baseline rate limit and a burst capacity limit. If users exceed this limit, API Gateway instantly steps in and throws a 429 too many requests error. It basically acts as a shock absorber, deliberately sacrificing a few requests to keep your backend servers alive. But watch out for this trap. Whether you're taking the DVA-C02 exam or working out in production, it is the proxy integration trap. AWS gives you 2 distinct ways to configure that integration request step we talked about. You can use custom integration, where you manually write those mapping templates to transform the payload.
Or you can choose proxy integration. If you choose proxy integration, API Gateway basically fires the receptionist. It takes the entire raw HTTP request, headers, body, query strings, everything, shoves it into a massive JSON object, and passes it directly to the backend. You bypass mapping templates completely. So if you need the absolute fastest way to pass everything straight through with zero transformation, you always choose proxy integration.
All right, let's lock this down. Here are your 3 rapid takeaways. 1. API Gateway isolates your backend by handling authentication, throttling, and request validation right at the edge. 2. The request lifecycle flows sequentially through the method request, the integration request, out to the backend, and back through the response phases. And 3. You use stage variables to dynamically route traffic to different backend environments without ever rewriting your API.
I want to leave you with one final warning. Never expose a public API Gateway endpoint without attaching an authorizer and a strict throttling limit. If you do, you aren't building an API. You are building a target.
Welcome to this explainer. Okay, let's dive right into this. You build a serverless checkout API. A user clicks Buy. The API spins, and after 30 seconds, it throws a 504 gateway timeout error. The user is frustrated. But 10 minutes later, they look at their bank account and realize their credit card still got charged. Why? Because you treated your API like a magic box, and you didn't understand how API Gateway actually invokes your Lambda function. Let me show you exactly what is happening under the hood. When you connect API Gateway to AWS Lambda, they communicate using a strictly synchronous invocation. API Gateway is making a live phone call to Lambda. It opens a connection, hands over the HTTP request, and then stands there, holding the line, waiting for Lambda to finish executing and hand back a response. When that request hits API Gateway, it passes through authentication and enters the integration phase. This is where the request gets prepared for Lambda. As an AWS developer, you have a massive architectural choice to make right here: custom integration or proxy integration. If you choose custom integration, you are taking the hard road. You have to manually write Apache velocity mapping templates. You have to write code inside API Gateway to explicitly pluck out the headers, the query string parameters, and the JSON body, and then map them into a custom JSON payload that your Lambda function expects. It gives you absolute control, but it is heavy and complex to maintain. But if you check the box for Lambda proxy integration, API Gateway does all the heavy lifting. It takes the entire raw HTTP request, the path parameters, the headers, the query strings, the source IP, and the body, stuffs it all into one giant JSON object called the event, and hurls it directly at your Lambda function. Think about that. Your Lambda function's event object instantly contains live web traffic. You just write event.queryParameters or event.body in your code, and you have exactly what the user sent. It is the absolute fastest way to build a REST API. But here's where people fail. They use proxy integration, their Lambda successfully processes a database rate, and then their code simply returns the string success. Immediately, API Gateway throws a 502 bad gateway error back to the client. Why? Because with proxy integration, you fired the receptionist. API Gateway is no longer formatting the response for you. It expects your Lambda function to return a very strictly formatted JSON object. To implement this correctly, your Lambda code must return an object containing an integer status code, a headers object, and a stringified JSON body. If you just return raw text, or if you forget to stringify the body, API Gateway panics, breaks the connection, and fails the request. You own the HTTP response now. Now imagine this. Your API triggers a Lambda function that processes a massive video file. The code works perfectly, but because the file is huge, it takes 45 seconds to run. Your API will fail every single time. Why? Because API Gateway has a hard, unchangeable, maximum integration timeout of exactly 29 seconds. Lambda functions can run for up to 15 minutes, but API Gateway does not care. At exactly 29 seconds, API Gateway will drop the connection and return a 504 gateway timeout to the user. But here is the DVA-C02 exam trap. Your Lambda function keeps running in the background. API Gateway severed the connection, but Lambda didn't stop. It finishes processing the video, it charges the credit card, but the user thinks it failed because they got a 504 error. This is exactly how you create duplicate transactions and corrupted system states. If your backend process takes longer than 29 seconds, you cannot use a synchronous API Gateway to Lambda integration. You must decouple it using SQS or EventBridge.
Also, you must understand how errors propagate. If you invoke Lambda asynchronously, like dropping a file in S3, Lambda automatically retries failures twice. But because API Gateway is synchronous, there are no automatic retries. If your Lambda function runs out of memory or crashes, API Gateway immediately hands a 5xx server error back to the client. It is entirely up to the front-end client application to implement retry logic with exponential backoff.
Finally, remember that cold starts directly impact your API latency. Because API Gateway holds the connection open, any delay Lambda experiences while initializing a new execution environment is directly passed to your user. If your Java function takes 4 seconds to cold start, your user is staring at a blank screen for 4 seconds. Let's lock this down. 3 rapid takeaways. 1. API Gateway invokes Lambda synchronously, holding the connection open and does not automatically retry failed requests. 2. Lambda proxy integration passes the entire HTTP request inside the event object, but requires your code to return a strictly formatted response containing a status code and stringified body. 3. API Gateway has a hard 29-second timeout, which will sever the connection and throw an error even if your Lambda function is still happily executing in the background. One final warning. Always catch your own errors in your Lambda code and return proper 4xx status codes for bad user input. If you let your code crash, AWS defaults to throwing a 502 or 500 error, making your system look broken and making it an absolute nightmare to debug in CloudWatch. So look at your own architecture today. Are you holding the line open on a 30-second process, just waiting for a timeout to happen?
All right, let's dive straight into this explainer. Picture this. It's Black Friday. You've just launched a massive 50% off sale, and the stakes are absolutely huge. Your entire year's revenue is literally on the line right now.
Then, exactly at midnight, 10,000 customers click checkout at the exact same second. Your front-end API gateway receives all of that massive traffic and immediately fires 10,000 synchronous requests straight through to your backend database.
And just like that, your database catches fire and dies. The entire site crashes completely. Millions of dollars in revenue, gone in a single second. So, why did this happen? Well, it's because you built a tightly coupled, synchronous system, and you didn't include a shock absorber.
Let me show you how we can actually protect our systems from these kinds of brutal traffic spikes. Amazon's Simple Queue Service, or SQS, is a managed message queue service that acts as exactly that, a shock absorber. Think of it as a buffer. You see, if you build an API that talks directly to a backend compute service or a database, they are tightly coupled, meaning if the database slows down, the API slows down right with it. If the database crashes, the API crashes. You know how a tightly coupled synchronous API gateway will just drop the connection and throw a brutal 504 gateway timeout if the backend takes longer than 29 seconds to respond? We fix all of that by decoupling the system.
To really picture this, let's think about a super busy coffee shop. The cashier taking your money is what we call the producer. The barista actually making your drink is the consumer. Now, if the cashier had to stop and make every single drink before taking the next customer's order, the line would literally go out the door and the whole system would grind to a halt. Instead, what do? The cashier just writes your order on a cup and sets it on a counter.
SQS is that counter. The producer, which is like your API gateway, takes the raw HTTP request, dumps a JSON message right onto the queue, and immediately returns a fast, safe success response to the user. The transaction is safely captured, it's fast, it's clean, and you get absolutely zero 504 timeouts.
Now let's see how this all comes together. The consumer, something like a Lambda function, pulls that queue. It pulls down messages in batches and processes them at its own safe, controlled speed. So if 10,000 messages hit the queue instantly, your fragile legacy database doesn't get crushed under the weight. The queue just gets a little longer. You completely prevent backend overload by processing everything asynchronously.
But listen closely, because this is where people really mess up. Developers will connect a Lambda function to process a batch of SQS messages. Let's say their code takes 40 seconds to process the data and update the database. But they left the queue's default visibility timeout set to 30 seconds.
This brings us to a really crucial point, understanding that visibility timeout. You see, when a consumer grabs a message from SQS, SQS doesn't actually delete it, it just hides it. That hiding period is the visibility timeout. SQS is basically just waiting there for your Lambda function to finish its work and send back an explicit delete command essentially saying, hey, I successfully processed this, please remove it now.
Let's walk through the timeline to see exactly how this blows up.
At 0 seconds, your first Lambda starts. But if your code takes 40 seconds to run and that timeout is only 30 seconds, well, SQS assumes your first Lambda function just died, so it unhides the message. Suddenly, right at the 30-second mark, a second Lambda environment comes along, grabs that exact same message, and starts duplicate processing. And boom! You just charged the customer's credit card twice. Think about that for a second. Your first Lambda is still running in the background, and your second Lambda just started processing the exact same order. Remember, standard SQS guarantees at least once delivery, meaning it absolutely will deliver duplicates occasionally. Because of this reality, as an AWS developer, you have to write your consumer code to be idempotent. That's a fancy word, but it just means writing a tiny little check into your database logic that says, hey, have I seen this transaction ID before? If yes, skip it. You literally must design your system assuming you are going to receive the exact same message more than once. Now, I want you to imagine another scenario. A user submits an order, but maybe they type an invalid, completely corrupted string of characters into their address field. Your Lambda function pulls the message, tries to parse the JSON data, and just crashes. The code totally fails. And because it failed, it never sends that delete command back to SQS. Eventually, the visibility timeout expires, and the message goes right back onto the queue. Another Lambda pulls it, and yep, it crashes again. This right here is what we call a poison message.
It will just loop continuously, literally burning through your AWS budget. It will sit there and consume all of your compute concurrency until the data finally expires, which could be days later. The emotional and financial pain of letting a poison message happen in a production environment is something you definitely want to avoid at all costs.
To handle this the right way, both for your AWS exams and in real-world production, you have got to configure a dead letter queue, or DLQ. Think of it as an isolation queue. You essentially configure your main queue to say, look, if this message fails to process 3 times, get it out of here and drop it into the DLQ. That way, your system automatically isolates the bad data. It keeps processing all the good orders seamlessly, and you can go in and inspect that corrupted message manually later on. But wait, what if you're processing something like a financial ledger? In that case, the exact order of transactions is absolutely critical, and you absolutely cannot tolerate any duplicates whatsoever. Standard SQS just isn't going to cut it here. For that, you need a first-in, first-out queue. That stands for first in, first out. Let's slow down for a second and really break down this massive trade-off. Standard queues scale practically infinitely, but they do handle duplicates. FIFO, on the other hand, guarantees strict ordering and automatic exact once processing. But, and this is a big but, FIFO queues have very strict hard throughput limits. So if you really need infinite scale, you have to use standard SQS and just handle the ordering and duplicates yourself in your own application code. There's another thing you need to watch out for: the Lambda batch failure trap. Here's how it works. If your Lambda pulls a batch of 10 messages from SQS, and let's say message number 8 happens to fail, Lambda will, by default, fail the entire batch. It sends all 10 messages right back to the queue for duplicate processing. Luckily, the solution is super simple, but it is absolutely essential. You just need to configure your Lambda event source mapping to report batch item failures. By doing this, it tells the system to only retry the single specific message that actually broke, rather than tossing out the whole batch. All right, let's lock this all down with 3 rapid takeaways. Number 1, SQS decouples producers and consumers. It acts as a shock-absorbing buffer to prevent massive traffic spikes from crashing your backend databases. Number 2, you use the visibility timeout to hide messages while they're processing, but you have got to make your code idempotent because standard SQS will deliver duplicates. And number 3, always implement a dead letter queue to catch those poison messages before they create infinite loops of crashing compute. I want to leave you with one final warning today. Don't use SQS if you actually need a synchronous response. If your front-end user is sitting there staring at a loading spinner, waiting to see if their specific credit card was approved right this exact second, SQS is just the wrong tool for the job. SQS is designed for safely taking the order and doing the heavy lifting out of sight, in the background. So the very next time you sit down to design an API, ask yourself, does my user really need to wait around for this?
All right, let's dive straight into this explainer. Picture this high-stakes scenario. Your brand new mobile game, it just got featured on the App Store. This is literally the moment you and your team have been waiting for.
Traffic spikes exponentially. You go from 100 concurrent users to 100,000 users in just 10 minutes.
Your traditional Amazon RDS database hits 100% CPU. Your connections max out entirely. And then the absolute worst happens. The game crashes. You are losing money, you are losing momentum, and you are losing players by the second. But hey, what if I told you there's a world where this panic doesn't even exist?
Section 1. The Paradigm Shift. Serverless NoSQL.
If you had built this game on Amazon DynamoDB, your users wouldn't have noticed a thing. No downtime, no lag, because it's fully serverless and feels instantly fast no matter the scale. But to really grasp this, we need to completely shift our mental model. You don't have traditional tables connected by complex foreign keys here. Instead, you just have three simple things: tables, items, and attributes. Think of a table simply as a bucket. It's the core container that holds all your unstructured data. Inside that bucket, you have items. An item is basically just a single record. If we stick to our game example, a single item would be one player's entire profile.
And finally, we have attributes. These are the specific data points living inside an item. Things like their username, their high score, and their current inventory. And really, that's it. Table, item, attribute. It's an incredibly streamlined structure.
Section 2. The core engine, partition keys.
So, how exactly does DynamoDB give you single-digit millisecond latency, whether you have 10 items or 10 billion items? Well, it all comes down to the partition key. Every single item must have a primary key. When you write data, DynamoDB takes that partition key, runs it through an internal hash function, and uses the output of that math to drop your item onto a specific physical storage server. And that physical server? That's called a partition.
Think about that for a second. DynamoDB does not search a massive hard drive to find your data. It uses the hash to mathematically calculate exactly which server holds your item, and it goes straight to it. If your table grows too big, DynamoDB just quietly adds more partitions in the background and spreads the data out. That, my friends, is true infinite horizontal scaling. To implement this correctly as an AWS developer, you design your access patterns using a composite key. And that's just your partition key plus a sort key. Imagine a game leaderboard. The partition key could be the game ID, and the sort key is the timestamp. DynamoDB stores all the items with the exact same game ID physically close together on the very same server, automatically sorted by the timestamp. This means you can instantly query for the latest scores without any heavy lifting.
Section 3. The traps, where developers fail.
Listen closely, because this is where people mess up, and it's a massive pitfall if you're taking the AWS DVA-C02 exam. Trap number 1, running a scan operation instead of a query. Let's slow down here, because the difference is absolutely critical. A query efficiently goes straight to the exact partition using a key. A scan literally reads every single item in the entire table up to 1 megabyte at a time, throws away what it doesn't need, and then gives you the result. It is incredibly dangerous. A single scan can consume your entire database throughput in 1 second and just crash your application. Always, always design your tables to use a query. The second trap is the hot partition. Let's say you build a voting app, and 90% of your users vote for option A. All that high traffic has the exact same partition key, which means it is all hitting the exact same physical server. That single server gets completely crushed, and DynamoDB throttles your requests, throwing a provisioned throughput exceeded exception. So what's the solution? You must design high cardinality partition keys. All that means is choosing a key with a vast number of unique values, like a unique user ID, for example. Doing this evenly distributes the traffic across all your partitions, keeping your database healthy and blazing fast.
Section 4. Managing read and write capacity units.
How do you actually manage the capacity and the cost for all this speed? Well, you do it using read capacity units, or RCUs, and write capacity units, or WCUs. Let's break down the reads. One RCU gets you one strongly consistent read per second for an item up to 4 kilobytes. But by default, DynamoDB uses eventually consistent reads. Because it replicates your data synchronously across 3 availability zones, if you read data immediately after writing it, you might hit a replica that hasn't fully updated yet. If you absolutely must have the latest data, you request a strongly consistent read. But watch out, that strongly consistent read costs twice as many RCUs. It's a double cost penalty.
So, the crucial point here is choosing the right capacity mode. If your traffic is totally unpredictable, you use on-demand capacity. It scales instantly and you just pay per request. If your traffic is predictable, you use provisioned capacity with autoscaling to save money. But what if you get a sudden tiny spike? Don't worry, DynamoDB has your back with burst capacity, retaining up to 5 minutes of unused capacity to absorb the shock. Section 5. The next level. Event-driven architecture. Imagine a player buys a powerful new sword in your game. You need to update their inventory, send them a confirmation email, and unlock a new achievement. Doing all of that synchronously, that's going to slow down the entire game. Instead, you build a perfectly decoupled flow using DynamoDB streams. Here's exactly how it works. Step 1. The item changes in DynamoDB. Step 2. The stream instantly captures the before and after image of that item and drops it into a time-ordered log. Step 3. You connect that stream directly to an AWS Lambda function. The Lambda wakes up, sees the change, and asynchronously sends the email and unlocks the achievement. Your primary database stays instantly fast and completely unbothered.
Section 6. The 3 rules of NoSQL.
All right, let's lock this down with a rapid-fire recap. Rule 1. DynamoDB achieves single-digit millisecond latency by hashing the partition key to instantly locate the exact physical server holding your data. Rule 2. Never use a scan operation on a large table. Seriously, always design your access patterns to use efficient query operations. And Rule 3. Prevent hot partitions and throttling exceptions by choosing high cardinality partition keys. This will evenly distribute your read and write capacity units. I want to leave you with one final, firm warning. DynamoDB is not a drop-in replacement for a relational database. If you try to build complex SQL joins in DynamoDB, you will fail. In NoSQL, you design your table for the exact questions you need to ask, not just the data you need to store. So the next time you're architecting an app, ask yourself, are you just storing data, or are you designing for infinite scale?
Okay, picture this. You're building a new app, and you decide to treat DynamoDB exactly like a traditional SQL database, right? So you write a standard query to fetch all users currently in the active status, you confidently deploy your Lambda function, and you head out to lunch thinking, hey, everything is perfectly fine. But fast forward a week later, suddenly your app is throwing timeout errors, and your AWS bill has literally skyrocketed to thousands of dollars. Why did this happen? Well, because under the hood, you used a scan instead of a query, and you just learned the absolute hard way that relational database thinking completely fails in NoSQL. So in this explainer, we're going to look at exactly how DynamoDB retrieves data. We'll see why one method stays instantly fast, while the other basically flattens your performance like a steamroller. You see, in a traditional relational database, you just write a select statement with a where clause, and the database engine does all the heavy lifting to figure it out. But in DynamoDB, you are forced to choose between two distinct, totally different API operations to retrieve multiple items, and those are query and scan. Now, a query operation is surgically precise. To even use a query, you are absolutely required to provide the exact partition key using a key condition expression. When you do that, DynamoDB takes that partition key, runs it right through an internal hash function, and instantly locates the exact physical partition on the storage layer where your specific data lives. Because of this direct routing, it really doesn't matter if your table has 10 items or 10 billion items. It just goes straight to the data. Once it's there, you can optionally use the sort key with a comparison operator to fine-tune those results, like, say, finding only the orders placed in the last 7 days. Because it only ever accesses the exact data you actually need, a query is incredibly efficient and super cost-effective. But a scan? Well, a scan is the exact opposite. It is a total brute force operation. Instead of going to a specific partition, it just starts at the very beginning of your table and it reads every single item, page by page, across the entire database. I want you to think about that for a second. If your table has grown to 50 gigabytes of data, a scan operation reads all 50 gigabytes straight off the disk, even if you're only trying to locate one single specific user. It is just incredibly wasteful. And guys, here is where so many developers fail. I mean, both on the AWS DVA-C02 exam and in actual production environments. They realize the scan is returning way too much data, right? So they attach a filter expression to their code. They assume this acts kind of like a SQL where clause and that it's going to save them money and capacity. Let me be perfectly clear. It will not. Here's exactly why this filter trap catches people. You see, a filter expression is applied after the scan finishes reading the data from the table, but before those results are actually returned to your application. This means you are still charged read capacity units, or RCUs, for reading the entire table off the disk. A single scan on a massive table can consume your entire provisioned throughput in one go. That causes severe throttling, and ultimately, it's going to crash your live application.
Now, let's imagine a slightly different scenario. You've got a nightly analytics job that actually does need to process every single item in the table. So you run a standard scan, but you hit a huge bottleneck. A single scan operation reads sequentially, and it is hard-capped at returning a maximum of 1 megabyte of data at a time. For a massive table, that is just way too slow.
So, looking for a speed boost, you configure a parallel scan. You provide segment and total segments parameters in your code. This logically divides the table into smaller chunks, which lets you deploy multiple worker threads to scan those segments simultaneously, all in parallel. Problem solved, right? Well, your analytics job finishes quickly, sure, but suddenly your pagers start going off. Your production API is completely down. Why? Because your parallel scan just forcefully consumed all the table's RCUs. It created massive hot partitions across your database, totally starving your live customer-facing application of the read capacity it desperately needed to function. As an AWS developer, you absolutely must avoid running parallel scans if your table is already dealing with heavy read and write activity from real production traffic. So, how do we actually fix this? I mean, if scans are so dangerous, how do you query data efficiently if you simply don't have the partition key to begin with? The answer is actually pretty elegant. You build a global secondary index, commonly known as a GSI. You can think of a GSI as essentially a shadow copy of your table, one that's automatically maintained and synchronized entirely by DynamoDB in the background. When you create a GSI, you actually get to choose a brand new partition key and sort key. DynamoDB takes your existing data and projects it into this completely new structure for you. So now, instead of running a crazy expensive scan across your main table, you can run a highly efficient targeted query operation directly against the GSI using your new keys. It's a real game changer. But wait, before you go deploy that, you really need to watch out for the pagination trap. Remember that 1 megabyte limit we talked about earlier? Because both query and scan operations strictly stop after retrieving 1 megabyte of data, you can never, ever safely assume your code retrieved all the matching results in a single API call. If there's more data waiting to be read beyond that 1 megabyte limit, DynamoDB is going to return a special element called last evaluated key in its response. Your Lambda code absolutely must actively check for the presence of this key. And if it exists, you just pass it back into your next API request as the exclusive start key to continue paginating through the rest of the results. All right, let's lock this all down. Here are your 3 rapid takeaways. Number 1, a query uses the partition key to instantly find data, while a scan brute forces the entire table and just burns through massive amounts of read capacity. Number 2, filter expressions only remove data from the final response. They do not save you from paying the RCUs for reading all that data off the disk. And number 3, if you need to search on non-key attributes efficiently, just skip the scan entirely and create a global secondary index. Okay, one final insight for the road. If your queries are perfectly optimized but they're still causing a heavy database load, and your application can tolerate eventually consistent reads, put Amazon DynamoDB Accelerator, or DAX, in front of your table. DAX is an in-memory cache that drops your read latency from milliseconds down to microseconds. It drastically reduces the load on your database, all without requiring you to rewrite any of your query logic. So I want you to look at your own codebase today. Are you surgically querying your data, or are you secretly brute forcing your way to your next massive AWS bill? Picture this: a user transfers $1,000 out of their account. It's a high-stakes moment, right? But a millisecond later, their mobile app refreshes, and that $1,000 is still just sitting there. Thinking the transfer completely failed, they panic. So, what do? They click send again. Well, guess what? You just double charged them, you overdrew their accounts, and you completely ruined their day. So why did this disaster actually happen? It happened because of a fundamental misunderstanding of how DynamoDB replicates data under the hood. Your application just got hit by a stale read. In this explainer, we're going to dive right into exactly how DynamoDB consistency works in distributed systems. We'll unpack the exact reason why your database occasionally lies to you, because, let's be real, it's not magic, it's architecture. To really understand this, we have to look at the baseline mechanics. When you write a piece of data to DynamoDB, it doesn't just save it to a single hard drive and call it a day. To guarantee extreme durability, DynamoDB synchronously replicates your data across 3 physically isolated availability zones within an AWS region. Let's walk through how this process actually works. When your application executes a put item or update item request, DynamoDB first writes that data to the primary storage node. Next, it sends the data out to the secondary nodes. And as soon as a majority of those nodes acknowledge the write, DynamoDB tells your application, success. Your code moves on, thinking everything is fully complete and locked in.
But here is the catch. There is a tiny microsecond gap before that data fully propagates to the final node in the cluster. It's an almost imperceptible window of time. But in a high-traffic application, that tiny window is a massive hole. When you go to read that data back, AWS gives you a massive architectural choice. You are basically choosing between pure speed and absolute accuracy. Let's break these two down. By default, DynamoDB performs what's called an eventually consistent read. With this type of read, DynamoDB routes your request to a randomly selected storage node. Now, this is incredibly fast and highly efficient, but if the system happens to query that one secondary node that hasn't received the latest update yet, it's going to hand you the old, stale version of the data. Now, on the flip side, if your application absolutely cannot tolerate stale data, like our bank transfer example earlier, you have to explicitly configure your API call to perform a strongly consistent read. When you do this, DynamoDB forces the read to verify the latest state across all the nodes. It guarantees that you will receive the most up-to-date data, reflecting all successful prior write operations. It's perfectly accurate.
So you might be wondering, why wouldn't you just use strongly consistent reads for absolutely everything? I mean, it sounds like the safest bet, right? Well, it really comes down to two major trade-offs: cost and scalability.
Let's talk about the cost first. In DynamoDB, throughput is billed in read capacity units, or RCUs. One RCU gives you exactly one strongly consistent read per second for an item up to 4 kilobytes. But that exact same RCU will give you 2 eventually consistent reads. It's literally a 2-for-1 deal. If you default your entire application to strong consistency just because you're playing it safe, you are instantly doubling your AWS database bill. Let that financial impact sink in for a moment.
Now, let's talk about scalability. This is the famous CAP theorem in action in the real world. If there's a network blip or an availability zone outage, a strongly consistent read might not be able to securely verify the latest state across the cluster. And instead of risking giving you old data, DynamoDB will just throw an HTTP 500 server error and fail. Your application literally goes down. An eventually consistent read, however, handles that exact same network blip gracefully. It will still succeed by giving you whatever data it has currently available. By accepting eventual consistency, you are trading a tiny bit of accuracy for massive bulletproof availability.
Think about that for a second. If your AWS Lambda function processes an e-commerce order and instantly tries to read the user's updated profile to generate an email receipt, well, an eventually consistent read might pull the pre-order state. Your receipt will show the wrong data, and you're going to confuse the customer. For immediate read-after-write flows within the same function, you absolutely must enable strong consistency. But on the other hand, if you're just loading a social media feed or a product catalog, nobody cares if a comment or a review takes 200 extra milliseconds to show up. Use eventual consistency and save those RCUs.
Section 1, Exam and Production Traps. This is where developers fail on the DVA-C02 exam, and much more importantly, in the real world.
Here's a classic mistake. A team builds a global secondary index, or GSI, to query their data in a totally new way. They test it out, they realize their data is occasionally stale, so they update their code to request a strongly consistent read against the GSI, and the code instantly breaks. Why? Because a global secondary index is effectively a shadow table. When you write to the base table, DynamoDB updates the GSI asynchronously in the background. Because of this structural, architectural decoupling, you simply cannot perform a strongly consistent read on a GSI. It is physically impossible. GSIs only support eventual consistency, period.
Now, imagine this scenario. You have a massive global application spanning across New York and London. You smartly use DynamoDB global tables to keep the data synced across continents. A user updates their profile in New York, and a Lambda function in London reads that profile a split second later. The data is old.
So, why did that happen? It happened because global tables use storage-based asynchronous replication across AWS regions. While it typically syncs in well under a second, there is a hard rule you absolutely need to memorize. Cross-region strong consistency does not exist. You only get strong consistency within the local region.
Finally, as your smart friend trying to save you from a massive architectural failure, I have to warn you about the DAX trap. DynamoDB Accelerator, or DAX, is a brilliant in-memory cache designed to give you microsecond read performance. But if you execute a strongly consistent read through a DAX cluster, DAX is forced to completely bypass the cache and hit the underlying DynamoDB table directly to guarantee accuracy. If you're relying on DAX to magically lower your latency, but you force strong consistency on every single read out of fear, you are completely defeating the purpose of the cache.
All right, let's lock this down and summarize. Here are 3 rapid takeaways to remember. Number 1, eventual consistency is a DynamoDB default. It's twice as cheap and highly available, but it can return stale data due to microsecond replication lag. Number 2, strongly consistent reads guarantee you get the absolute latest data, but they consume double the read capacity units and can actually fail during network disruptions. And number 3, global secondary indexes and cross-region global tables update asynchronously and exclusively support eventually consistent reads.
One final warning before we wrap up. Never default to strong consistency just because you're scared of stale data. If you design your application to tolerate eventual consistency wherever possible, your system will be infinitely more scalable, resilient, and cost-effective. So the next time you build a feature, ask yourself, is absolute perfection really worth taking your entire system offline?
A user transfers $500 to a friend. Your API deducts $500 from their account. Right before you add the money to the friend's account, your back-end server crashes.
Section 1. The missing money problem. When that server crashes, the money is gone forever. Your customer is furious, and you're facing a massive financial compliance nightmare.
Why? Because you didn't build your database rights to be atomic. Today, we're covering the missing money problem, DynamoDB transactions, the two-phase commit trap, race conditions, cost and scaling limits, and the consistency illusion. Let me show you how to actually fix this and why even the fix can fail if you don't understand how it works under the hood.
Section 2. Enter DynamoDB transactions. To solve the missing money problem, you use Amazon DynamoDB transactions. Transactions provide atomicity, consistency, isolation, and durability, or ACID, in DynamoDB. But let's simplify that. It just means all or nothing.
Amazon DynamoDB transactions simplify the developer experience of making coordinated all-or-nothing changes to multiple items, both within and across tables. With the Transaction Write API, you can group multiple put, update, delete, and condition check actions.
You submit these actions as a single transact write items operation that either completely succeeds or completely fails as a single unit. The exact same is true for multiple get actions, which you group and submit as a single transact get items operation.
Section 3. The two-phase commit trap. So you write the code, you group the deduction and the deposit, you deploy to production. You think you're safe.
But suddenly, during a massive flash sale, your error logs light up with transaction canceled exception. Your system is failing.
Here is exactly what is happening and why transactions still fail. DynamoDB performs 2 underlying reads or writes of every item in the transaction, one to prepare the transaction and one to commit the transaction.
Section 4. Handling race conditions. Think about that two-phase commit process for a second.
It's a two-phase commit. DynamoDB locks the items, verifies that no other process is modifying them, and then writes the data. But what if user A and user B both click buy on the absolute last concert ticket at the exact same millisecond? This is a race condition. Both requests trigger a transact write items call. Both check the condition that the ticket is still available. One request wins the race and commits the change. The second request hits the prepare phase, realizes the item has been modified by the first request, and violently rejects the write, throwing a transaction canceled exception.
This is where optimistic locking comes in. Optimistic locking is a strategy to ensure that the client-side item that you're updating is exactly the same as the item currently in Amazon DynamoDB. It protects database rights from being overwritten by the rights of others, and vice versa.
But when a conflict happens, DynamoDB doesn't magically queue up the failed transaction and wait. It just fails. As an AWS developer, you must write custom logic in your application to catch that exception, reread the database to get the latest state, and decide if you should attempt the transaction again.
And if you do try again, you must use exponential backoff. In addition to simple retries, all AWS SDKs use exponential backoff. Progressively longer waits will occur between retries for improved flow control. If you just hammer the database with instant retries, you'll cause a massive throttling cascade.
Section 5. Cost and scaling limits. Now let's talk about these cost and scaling traps. This is heavily tested on the DVA-C02 exam.
Because of that two-phase prepare and commit process, transactions cost double. Transactional write requests require 2 write capacity units, or WCUs, to perform 1 write per second for items up to 1 kilobyte. Transactional read requests require 2 read capacity units, or RCUs, to perform 1 read per second for items up to 4 kilobytes.
If your table normally consumes 1,000 WCUs and you wrap all your code in transactions just to be safe, you instantly need 2,000 WCUs to do the exact same amount of work. Your latency goes up and your AWS bill doubles.
Also, watch out for the physical limits. A single transact write items or transact get items request has a hard limit of exactly 100 items.
And the total payload cannot exceed 4 megabytes. I want to be clear, this information is a strict architectural constraint you must memorize. If you try to process an order with 101 items in the shopping cart, the API call will be rejected. You cannot use transactions for massive bulk data operations.
Section 6. The consistency illusion. Now imagine this. Your transaction completely succeeds. The money is transferred. A Lambda function listening to DynamoDB streams wakes up to send an email receipt. DynamoDB streams captures a time-ordered sequence of item-level modifications in any DynamoDB table and stores this information in a log.
The Lambda function reads the stream, then queries a global secondary index to get the user's profile data to send the email. But the email goes to the wrong address. Why? Because even though the transaction was strongly consistent on the base table, global secondary indexes update asynchronously. The GSI is still eventually consistent. Your transaction succeeded, but the rest of your distributed system hasn't caught up yet.
Let's lock this down. 3 rapid takeaways. 1. Transact write items provides ACID compliance and all-or-nothing execution, but costs exactly double the WCUs and RCUs due to the two-phase commit process. 2. Transactions will fail with a transactions canceled exception during concurrent write conflicts, requiring you to implement optimistic locking and exponential backoff in your application code. 3. Transactions are strictly limited to 100 items and 4 megabytes per request, and while they guarantee consistency on the base table, downstream replicas and GSIs remain eventually consistent.
One final warning. Never use transactions as a default crunch. Only pay the double capacity cost and latency penalty when your business logic absolutely demands strict multi-item atomicity. Look at your own code today. Are you building truly atomic systems, or are you just paying double for a false sense of security? You open the AWS console. You create a folder in your brand new S3 bucket, drop a crucial image file inside, and then your application code tries to traverse the directory tree to find it. And then the code crashes. It completely breaks down. So why did that happen? Well, it's because you treated S3 like a standard hard drive. And in doing so, you fell for the single greatest illusion in all of AWS. The truth is, S3 folders are totally fake. They just do not exist. Let's dive right into how S3 actually works under the hood so you never make this mistake again. Let's get this straight right off the bat. Amazon S3 is not a file system. You can't install an operating system on it, and you definitely can't mount it like a traditional drive. It's an object store. In a normal file system, data lives in a strict physical hierarchy. You've got main directories nested inside other directories, kind of like a giant filing cabinet. But in S3, it's a completely flat namespace architecture. You essentially just have 2 things. You have a bucket, which is simply a region-specific container, and you have objects, which are just your raw files and their associated metadata, all living side by side.
Now, you might be wondering, how did you just create a folder in the AWS console? The reality is, you didn't. What you actually created was an object with a very specific key. The key is simply the unique flat name of the object. If you name an object images/profile/user.jpg, the AWS console sees those forward slashes and pretends it's a folder structure, really just to make your human brain happy. But to S3's backend, that entire string is just one single flat identifier.
Because S3 is a flat object store, it relies entirely on the web. It's completely API-driven. Every single time your application uploads, downloads, or deletes a file, it's making synchronous REST API calls over HTTP. Specifically, you're making put, get, and delete operations.
Think about that for a second. Your code isn't moving files around on a local physical disk. It is interacting with a highly distributed, massive web service. Because of this fundamental difference, Amazon S3 automatically scales to handle absurdly high request rates. It distributes your objects redundantly across multiple availability zones to guarantee what AWS calls 11 nines of durability. That is 99.9999999%. To put that into perspective, if you stored 10 million objects in S3, you can expect to lose a single file once every 10,000 years. S3 also provides strong read-after-write consistency. That means the absolute millisecond you receive an HTTP 200 success response from a put request, that new object is immediately available to read worldwide.
But here is where everyday developers fail in production. Imagine you let your users upload massive 5 GB video files using a standard, basic put request. The upload crawls along, taking 20 long minutes. Then, the user's cell network blips at minute 19. The request fails, and you have to start all over from byte 0. It is a horrible user experience and, honestly, a massive waste of time and money.
To implement this correctly as an AWS developer, you absolutely must use multi-part uploads. For literally any file over 100 megabytes, you use the AWS SDK to break the file into tiny chunks and upload them in parallel. If one single chunk fails because of a network drop, you don't start over. You just retry that one tiny piece. It's infinitely faster, highly optimized, and far more resilient.
Now imagine this really common scenario. A user uploads a profile picture and you instantly need to resize it to a thumbnail. If you process that image synchronously on your backend web server while the user waits, a sudden viral spike in uploads is going to completely choke your compute resources and bring your app down. Instead, the AWS way is to build an event-driven architecture using S3 event notifications.
Here's how that flows. When a new object lands in the bucket, S3 instantly detects the put operation. It immediately fires an event directly to an AWS Lambda function, an SQS queue, or an SNS topic. Your Lambda function then wakes up asynchronously, resizes the image in the background, and saves the thumbnail back to S3. And the best part? Your main server never even knew it happened. It just kept running perfectly smoothly.
Now, let's pivot just a bit. You really need to watch out for the security and access traps here, especially if you're studying for the DVA-C02 exam. This right here, this is exactly where people mess up and accidentally leave data exposed.
For example, how do you grant a mobile app user temporary access to upload a file to a deeply private bucket without hard-coding your permanent AWS credentials directly into your app? You use a pre-signed URL. Your secure backend generates a cryptographic, time-limited link and hands it to the client. The client then uses that exact URL to upload the file directly to S3. No credentials shared, fully secure. It's a real game changer.
What about protecting your data from yourself? If you accidentally overwrite or delete a critical file, S3 offers a feature called versioning. But here's the trick you need to remember. When versioning is enabled and you hit delete on an object, S3 doesn't actually destroy the data. It simply places a delete marker on top of it, making it invisible to standard GET requests. The old version is still sitting right there, and you are still paying for it every single month. To stop your AWS bill from exploding due to all those hidden versions, you have to configure a lifecycle policy. You set an automated rule that essentially says, Day 0, stored in S3 standard. After 30 days, automatically move those old versions to S3 standard infrequent access to save a big chunk of money. Then, after 90 days, transition them entirely to S3 Glacier, where storage costs just pennies, but retrieval takes a few hours. Or, if you have absolutely no idea what your access patterns look like, maybe a file is hot one week and totally ignored the next, you can just use S3 Intelligent Tiering. This storage class automatically monitors and moves objects between tiers for you based on exactly how often they're actually accessed, optimizing your costs without you having to lift a single finger.
Finally, you need to remember the critical difference between IAM policies and bucket policies. IAM policies dictate what a specific user or role can do across AWS. Bucket policies, on the other hand, attach directly to the S3 bucket resource itself. This fundamental difference makes the bucket policy the absolute perfect place to enforce strict global rules. Things like completely blocking unencrypted uploads or enforcing the public access block to ensure absolutely nobody can accidentally expose your private data to the public internet.
Okay, let's lock this down. Here are 3 rapid takeaways from this explainer.
Takeaway number 1. S3 is a flat object store, not a traditional file system. Folders do not exist. They are just an illusion created by forward slashes in your object key.
Takeaway number 2.
You must optimize your performance and reliability by using multi-part uploads for large files, and secure your access by using pre-signed URLs to give clients direct, temporary access to your buckets.
Takeaway number 3. You control your growing costs by using lifecycle policies to transition data to cheaper storage classes like Glacier. And you protect that data by combining S3 versioning with a solid understanding of delete markers.
And one final warning before we go. S3 has an amazing feature for static website hosting, but it only hosts static files like HTML, CSS, and client-side JavaScript. If you try to upload server-side code like PHP or Node.js, S3 will not execute it. It's just going to let the user download your raw source code, exposing your entire backend logic to the world. So the next time you're building in the cloud, ask yourself, are you still treating AWS like a dusty old hard drive, or are you ready to actually harness the power of a highly distributed object store?
Okay, picture this. You've got a content creator uploading a massive 4 gigabyte 4K video to your platform. They're stuck on hotel Wi-Fi, and the upload is taking an entire hour. And then, at exactly 99%, the Wi-Fi blips, just for 2 seconds. The connection drops, your server returns an error, and bam! They have to start that entire 1-hour upload completely from scratch. You can bet they are absolutely furious.
So why did this happen? Well, it's because you used a standard S3 put operation for a massive file. When you upload a file this way, it sends the data as a single continuous stream. So if that network connection drops for even a fraction of a second, that stream is severed. S3 just discards whatever incomplete data it received, the upload fails entirely, and basically, you've engineered a system that was destined to fail. But don't worry, let me show you how to actually engineer resilient storage pipelines.
Okay, let's dive into this. Section 1. The solution, S3 multi-part uploads.
Instead of relying on one fragile stream, this architectural fix breaks your large file into dozens, hundreds, or even thousands of smaller chunks and uploads them completely independently. Now, AWS highly recommends using multi-part uploads for literally anything over 100 megabytes. But hear me clearly on this. It is a strict, undeniable, hard requirement for any file larger than 5 gigabytes. You literally cannot upload a 6 gigabyte file with a standard put operation. S3 will just outright reject it. And this brilliantly illustrates the difference. Think of it kind of like moving to a new city. A standard put request, that's like packing absolutely everything you own into one massive semi-truck. If that single truck breaks down on the highway, well, absolutely nothing reaches your new house. A multi-part upload, on the other hand, is like packing your belongings into a resilient fleet of 100 small delivery vans. If one van gets a flat tire, no big deal. The other 99 vans still arrive right on time, and you just send a replacement van for the one that failed.
All right, moving on to Section 2, Under the Hood, the architecture. Let's look at the exact mechanics happening behind the scenes here. So how do we actually build this fleet of vans? Well, behind the scenes at the API level, it's a very precise 3-step process. Step 1, your application code makes a request to S3 to initiate the upload. S3 responds by handing you a unique upload ID. Step 2, you split the file. Your code breaks that massive video into smaller chunks, usually somewhere between 5 megabytes and a few dozen megabytes, and pushes them to S3 in parallel. Every single time you upload a chunk, you include that unique upload ID and a specific part number, like part 1, part 2, and so on. Finally, step 3 is the assembly. Once every single part has successfully reached AWS, your application sends a complete multi-part upload request. S3 takes all those individual chunks, stitches them together in the exact order of their part numbers, and creates one single, seamless object in your bucket.
Think about that for a second. You aren't just surviving network drops here. You are fundamentally changing the performance profile of your application. Because the parts are uploaded independently, you can upload them in parallel. If you've got a massive bandwidth pipe, you can push 20 parts at the exact same time, which drastically reduces the total upload duration. And hey, if part number 17 fails because of a network blip, you don't restart the whole gigabyte file, you just retry that specific 5 megabyte part number 17. The resiliency is built directly into the architecture.
Okay, let's jump to Section 3, Scaling with Pre-signed URLs.
Now, we absolutely need to talk about scaling. Imagine routing a massive 4 gigabyte video upload through your small backend EC2 server. You're going to completely crush your compute resources and max out your network cards. It's a disaster waiting to happen. To bypass these backend bottlenecks, you combine multi-part uploads with pre-signed URLs.
Basically, your lightweight backend generates a unique, secure, pre-signed URL for every single part of that multi-part upload, and then hands those URLs back to the client's browser. The user's browser then uploads the file chunks directly to S3, completely bypassing your backend compute. Your servers stay fast, and S3 happily absorbs all that heavy network traffic.
And if those users are uploading from all across the world, you can take this a step further by enabling S3 transfer acceleration. What this does is route those individual multi-part chunks through the closest AWS edge location. So instead of fighting through public internet latency, your data rides the highly optimized AWS global backbone directly to your target bucket. It's incredibly fast.
Section 4. The hidden cost trap. Now, what's really interesting about this slide is this is exactly where things get dangerous. This introduces a massive exam trap. And honestly, it's the exact scenario where developers accidentally bankrupt their own companies. I'm talking about incomplete multi-part uploads. Think about it. What happens if a user starts an upload, pushes 3 gigabytes of chunks directly to S3, and then simply closes their laptop forever? The upload is never completed. S3 holds onto those hidden chunks, endlessly waiting for that complete multi-part upload command. You actually cannot see these chunks in the standard AWS console, but you are absolutely being billed for their storage space. Over months, these abandoned, invisible chunks can cost your company thousands of dollars. You have to protect yourself here. Now, if an upload fails permanently, your code should call the abort multi-part upload API to delete the stored chunks. But let's be real. You can never trust client applications to always clean up their messes. So you absolutely must configure an S3 lifecycle rule. You create a rule acting as an automated garbage collector, explicitly set to delete expired incomplete multi-part uploads after a certain amount of days, say 7 days. This automatically wipes out those abandoned chunks and protects your AWS bill. While we're talking about traps, you've got to watch out for the E-tag trap. If you're doing file integrity validation, be warned. For a standard upload, the S3 E-tag is usually just the MD5 hash of the file, but for a multi-part upload, the E-tag is not the MD5 hash of the entire file. Actually, it's a calculated hash of the individual part hashes, and it always ends with a dash and the total number of parts, like -24. You absolutely must account for this in your application code, or your integrity checks will fail every time. Finally, let's remember how this fits into your event-driven architecture. S3 event notifications will not fire when individual parts arrive. S3 waits patiently until the complete multi-part upload API call finishes stitching the entire file together, and then it fires a single S3 object created event. This is the exact trigger you use to wake up an AWS Lambda function to automatically start transcoding that video for your viewers. All right, let's wrap this up. Section 5, 3 rapid takeaways. So, the crucial point is this. Number 1, multi-part uploads are a hard, strict requirement for files over 5 gigabytes, and they dramatically improve your upload speed through parallelization. Number 2, you must implement S3 lifecycle policies to automatically delete incomplete multi-part uploads, or you are going to be permanently billed for invisible data. And number 3, combining pre-signed URLs with multi-part uploads protects your EC2 compute by allowing clients to upload massive files directly to S3. I'll leave you with one final warning. Never, ever assume a mobile network is stable. Always design your pipelines expecting the connection to drop. When you build this, write your client-side code so that it caches the upload ID, allowing it to retry exactly which part numbers drop, rather than forcing your users to start all over again. Build for failure, and you will achieve true resilience. Which kind of makes you wonder, what other silent bottlenecks are currently lurking in your cloud architecture? So picture this. You wake up to a phone call at 3 a.m. A security researcher just found your company's entire database of user profiles floating around on the public internet. You completely panic. You rush to check your AWS account, and sure enough, your Amazon S3 bucket is wide open. But how? You know for a fact you never clicked Make Public. Why did your files suddenly become public? Well, it's because S3 security is not just a single switch you can flip. It's actually a really complex web of overlapping permissions, and you just tangled yourself right up in it. It's almost never just one wrong click. It's usually a failure to understand how all these different security layers interact with each other. Okay, let's dive right into this explainer. I'm going to show you exactly how S3 permissions actually work in a real production environment, so you literally never leak data again. We're going to untangle this roadmap step by step. Identity versus resource policies, the legacy ACL trap, blocking public access, pre-signed URLs and encryption, and finally, VPC endpoints and auditing.
Section 1. Identity versus resource policies. The two doors of S3 security.
You have to understand that Amazon S3 is inherently paranoid. By default, every single bucket, every object, and every sub-resource is strictly private. The only entity that can access the data is the AWS account owner that actually created it. It's kind of like a massive bank vault where even the bank manager needs to scan their badge just to peek inside. To let anyone else in, you have to explicitly open the door. And there are really two main ways to open that door. First, you've got identity-based policies. These are your standard IAM or identity and access management permissions. You basically attach a policy to a user, a role, or even a Lambda function that says, hey, you are allowed to read from this bucket. Second, you have resource-based policies. These are your bucket policies. You attach a policy directly to the S3 bucket itself that says, I allow this specific external account to access my data. Now, AWS looks at both of these doors. If either one has an explicit allow, you get in. But here is the absolute golden rule of AWS security. An explicit deny always overrides an explicit allow. Let me repeat that, always. If your IAM policy allows access, but the bucket policy explicitly denies it, the request is completely blocked, period. You can hold all the right keys in your hand, but if the system explicitly says no, there's absolutely no way you're getting in.
Section 2. The legacy ACL trap, where developers fail.
Now, here is exactly where people mess up. They try to share a single file with a different AWS account. But instead of writing a nice, clean bucket policy, they use an access control list, or ACL. Guys, ACLs are a legacy nightmare. If an external user uploads a file to your bucket using an ACL, they actually own the object, not you. You can't even delete a malicious file from your own bucket. You are essentially paying AWS to store someone else's locked safe. To fix this, AWS created a feature called object ownership. As a developer, you absolutely must set this to bucket owner enforced. Doing this completely disables all ACLs across your entire bucket. From that exact moment on, every single object is owned by your account, and access is strictly controlled by modern IAM and bucket policies. You essentially take the power back.
Section 3. Blocking public access, the ultimate circuit breaker.
Think about that for a second. You can permanently lock down your data right at the account level. AWS gives you the block public access feature, and it acts as this ultimate circuit breaker. If you turn this on, it literally does not matter if a junior developer accidentally writes a bucket policy allowing the entire internet to read your files. S3 simply overrides it and blocks the traffic. It completely saves you from human error. But wait, what if you are hosting a static website on S3? Well, for a website to actually work, you must disable block public access, and you must write a bucket policy granting anonymous read access to your HTML files. But imagine if you accidentally store your private user database backups in that exact same website bucket. Suddenly, your private data is public to the world. So the rule here is incredibly simple. Never, ever mix public and private data in the exact same bucket.
Section 4. Pre-signed URLs and encryption. Secure temporary access.
Now, what's really interesting about this is, imagine this scenario. You have a strictly private bucket. Block public access is completely turned on, locked down tight. But you still need to let a customer download a specific PDF receipt, or maybe let a mobile app upload a video. How in the world do you do that when the doors are basically welded shut? Well, you use a pre-signed URL. Your backend code, which already has strict IAM permissions, generates a temporary cryptographically signed URL. You hand that link over to the client, and they have exactly 15 minutes to download or upload that single file directly to S3. You get to grant cross-account access without ever changing your bucket policies or exposing your backend architecture. It's exactly like giving someone a self-destructing VIP pass.
Now let's talk about encryption, because honestly, having access is only half the battle. You have encryption in transit and encryption at rest. To encrypt data in transit, you use a bucket policy with a specific condition that strictly denies any request where AWS Secure Transport is set to false. What does that mean in plain English? It means this forces all traffic to use secure SSL or TLS connections, completely rejecting anything that's unencrypted.
And for encryption at rest, you face a massive architectural choice, SSE S3 or SSE KMS. SSE S3 means Amazon automatically manages the encryption keys for you. It's totally easy and it's free. But SSE KMS means you manage the keys using the AWS Key Management Service. So why does this matter? Because with KMS,
every single time someone decrypts a file, that API call gets logged. You get this perfect audit trail of exactly who read your sensitive data and exactly when they did it. You don't just know the data is safe, you can actually prove it.
Section 5. VPC endpoints and auditing. Securing the private subnet. You really need to watch out for this incredibly common architectural trap. Let's say you have an EC2 server sitting in a private virtual private cloud, or VPC, subnet. It has absolutely no internet access whatsoever, but it still needs to write application logs to your Amazon S3 bucket. How does it connect? S3 is fundamentally a public service, so if your server doesn't have internet access, your upload just fails. The application crashes and your logs are totally lost. The solution here? You absolutely must configure a VPC gateway endpoint. Doing this creates a secure private tunnel from your internal network directly to S3, completely bypassing the public internet so your uploads never fail. Okay, let's lock this down. 3 rapid takeaways for you. 1. S3 is strictly private by default. Make sure you use bucket owner enforce to disable those legacy ACLs. 2. An explicit deny always overrides an explicit allow, and block public access is your ultimate safety net. And 3. Use pre-signed URLs to grant temporary, secure access without ever exposing your actual bucket to the public. I want to leave you with one final warning. If you aren't absolutely sure who has access to your data right now, run AWS IAM Access Analyzer. It will actively parse your policies and alert you the very second your private files are mathematically exposed. So really ask yourself, if I ran that analyzer on your company's AWS account right now, what would it find?
Okay, let's dive right into this. I want you to picture a scenario that is honestly every single developer's worst nightmare. It's the end of a long, exhausting day. You finally push your code to GitHub, you close your laptop, and you head to the kitchen to grab a well-deserved snack. But then, 5 minutes later, you get an email from Amazon.
You open the email, and your stomach just completely drops. Your AWS bill just spiked by $20,000 in 5 minutes. Why? How does that even happen? Well, it's because you left a tiny, seemingly harmless string of text in your repository. You hard-coded your AWS access keys into your script, and a malicious bot just scraped them, literally stealing your identity to spin up hundreds of massive, expensive EC2 instances to mine cryptocurrency entirely on your dime.
So let me show you how to actually give your applications secure access to AWS without ever touching a secret key. You see, when you, as a human being, log into the AWS Management Console, you use a standard password. But when your code needs to talk to AWS, like say a backend app trying to read a file from an S3 bucket, it relies on programmatic access keys. Now, these consist of 2 parts, an access key ID and a secret access key. The fatal mistake developers make is treating these keys like permanent passwords and just pasting them directly into their application code. If that code gets pushed to a public repository or even shared accidentally in a private Slack channel, your entire AWS account is completely compromised. Plus, because access keys are static, if you don't actively rotate them, they literally live forever.
Which brings us to the absolute golden rule for an AWS developer. And it is this. Applications should never store AWS credentials directly. Never. Let that sink in.
So naturally, you might be wondering, how does an application get permission then? We know it needs access to function, but we just established we absolutely cannot give it a permanent key. Well, this is where we pivot from a potential disaster to the smart, highly secure solution. You use IAM roles. Now, let's slow down here for a second to look at this comparison, because grasping this exact difference is absolutely essential. Think of an IAM user like an employee with a permanent ID badge. It belongs uniquely to them, and it works every single day until it's officially revoked by HR. But think of an IAM role more like a temporary contractor hat. A role does not have a permanent password, and it certainly does not have long-term access keys associated with it. It is simply an identity that a trusted entity can assume just to obtain temporary, short-lived security credentials for a specific job. Here is exactly how this works under the hood. Let's take an AWS Lambda function that needs to write data to a DynamoDB table. You don't bake a key into the deployment package. No way. Instead, you create an IAM role, specifically an execution role, and attach it to the function. Now here's where this gets really interesting. You don't just give the role a permissions policy to talk to DynamoDB. You must also configure a trust policy. The trust policy explicitly states who is allowed to wear the hat.
In this case, you literally tell AWS, I trust the Lambda service to assume this role.
Think about that for a second. Your code never handles the credentials directly. The AWS compute environment running your code assumes the identity entirely on your behalf.
Now, pay close attention here, because this is where people mess up. They successfully attach the role, but then they sit there trying to figure out how to manually extract or pass the credentials from the role into their actual Python or Node.js script.
You don't. Let's move to the next step and see how this builds out entirely automatically. Imagine this. Your Lambda function spins up. Because it has an execution role attached, the AWS environment automatically requests the temporary security credentials and injects them securely into the local environment, completely behind the scenes. Your AWS SDK, like Boto3 for Python, for example, is incredibly smart. When you write a single line of code to put an item in DynamoDB, you don't specify any credentials at all. The SDK automatically searches the local environment, finds those temporary keys, signs the API request, and executes it.
And this brilliantly illustrates a very simple, everyday concept. It is exactly like staying at a hotel. Think about it. You don't bring your own permanent deadbolt lock from home and attach it to your hotel room door, right? The front desk gives you a temporary digital key card. When you check out at the end of your stay, the card simply expires. If you happen to lose it down by the pool, the hotel just deactivates it instantly with zero risk to the actual building. That is exactly what an IAM role does for your compute resources.
Now, watch out for this exact trap in your exams and out there in real-world production environments. Let's say an application running on an EC2 instance needs to access S3. A developer creates an IAM user, generates long-term access keys, and places them in a shared credentials file right there on the server. Sure, the application works perfectly, but this is a critical security failure. If a bad actor compromises that EC2 instance, they can simply copy that file and use those permanent keys from anywhere in the world. As a responsible AWS developer, you must delete that user, delete those keys, create an IAM role with an S3 access policy, and attach it directly to the EC2 server. The AWS SDK will automatically rotate the temporary credentials in the background. You literally never manage a single key.
All right, let's lock this down. Here are your 3 rapid takeaways for this explainer. Number 1, never hardcode access keys in your application or store them on your compute instances, because leaked keys lead to instant account compromise. Number 2, use IAM roles for applications running on EC2 or Lambda to grant your code temporary automatically rotating security credentials. And number 3, remember that an IAM role requires both a permissions policy to define what actions are allowed and a trust policy to define which service or account is allowed to assume it.
One final warning before we wrap up. If you ever accidentally commit an access key to GitHub, do not just delete the commit and pretend it didn't happen. The bots have already scraped it. Immediately go into the AWS console, cut all API connections, and delete the key forever. So think about your own projects for a moment. Are you absolutely sure there are no hard-coded keys hiding in your code right now? Welcome to this explainer on mastering AWS IAM policies and permissions logic. Okay, we've got a lot of critical ground to cover today, so let's jump right in. Picture this scenario. You deploy a Lambda function that is simply supposed to read profile pictures from an Amazon S3 bucket. At first, the code works perfectly. But a week later, a completely unexpected bug in that exact same function accidentally executes a delete command and permanently wipes your entire production DynamoDB table. We're talking total failure, massive downtime, and a whole lot of lost money. So you have to ask yourself, how is that even physically possible? Well, it happens because you gave your code the wrong rules, simply because of a lack of understanding regarding how AWS actually decides what your app can access. Let me show you how to actually lock down your applications. You see, when your code runs on AWS, it assumes an identity, like an IAM role. But AWS doesn't really care who your app is. Authentication just proves identity. Authorization decides what that identity is actually allowed to do. And in AWS, authorization is completely governed by explicit JSON policy documents. These policies are simply AWS permission rules attached to your identities or your resources that explicitly state exactly what actions are allowed or denied. If you don't write the rule, AWS simply blocks the action. Think about it like a VIP pass at a massive music festival. Your physical IAM role is the badge around your neck. It gets you through the front gate. But when you try to walk into the backstage area, the security guard doesn't just look at your face.
They look at the back of your badge to read the strict list of rules that dictate your backstage access. If the rule says main stage only, you get rejected. AWS evaluates API requests the exact same way.
Section 1. The building blocks: effect, action, and resource.
Let's break down exactly how these rules are built. Every statement inside an IAM policy requires 3 specific building blocks. First, the effect. Is it an allow or a deny? Next, the action. This is the specific API call your code is trying to make. And finally, the resource. This is the exact target AWS entity identified by its Amazon resource name, or RN. To implement this correctly as an AWS developer, you've got to practice the principle of least privilege. If your app needs to read profile pictures, your policy should look exactly like this. Effect, allow. Action, S3 get object. Resource, the specific ARN of your images bucket, followed by a slash and a star to include the files inside it. Notice how you don't just grant full S3 access. You grant exactly one action on one specific bucket. Section 2. AWS Policy Evaluation Logic, the default state. So how does AWS evaluate these rules when your app is making thousands of API requests a second? Well, every single request across the account starts with an implicit deny by default. It's instantly blocked. But what if you have multiple policies in play? Imagine a frustrated developer trying to fix a bug who just attaches an administrator policy to the Lambda function, granting it full access to everything. But there is also a secondary policy attached that strictly denies DynamoDB access. What happens then? This brings us to the ultimate golden rule of AWS security. An explicit deny always overrides an explicit allow. Always. Think about that. You can write a policy to act as an absolute blast shield. You can create a rule that says, effect, deny, action, DynamoDB delete table, resource star. You attach that to your function. Now, even if someone accidentally attaches a full admin access policy to that exact same role, the AWS evaluation engine will see that explicit deny, immediately stop evaluating, and block the request entirely. The database survives. Section 3. The exam trap. Identity versus resource policies. Now, pay close attention, because this is where people mess up. A lot of developers only ever think about identity-based policies. That's the backpack of rules your Lambda function carries around with it. But AWS also heavily utilizes resource-based policies. Instead of attaching the rule to the Lambda function, you attach the rules directly to the Amazon S3 bucket itself. Now imagine this nightmare production scenario. You write a flawless identity-based policy, giving your Lambda function perfectly formatted permission to write data to an S3 bucket. You test it, and it fails. You get a 403 access denied error. You stare at your JSON code, and the allow rule is flawlessly written. So why did it fail? Because the developer who built the S3 bucket attached a resource-based policy directly on that bucket that explicitly denies all write access. This is a massive trap on the DVA-C02 developer exam, and obviously a disaster in the real world. When an identity tries to access a resource in the same AWS account, AWS evaluates both the identity policy and the resource policy. If either one has an explicit deny, it's a catastrophic failure. The request fails. If neither has an explicit allow, the request also fails due to the default implicit deny. You have to understand both sides of the equation to debug authorization failures. Okay, let's lock this down. 3 rapid takeaways. 1. Policies are JSON permission rules built on 3 core components: effect, action, and resource. 2. AWS evaluates requests using a strict logic where the default is an implicit deny, and an explicit deny will permanently override any explicit allow. 3. Applications are governed by both identity-based policies attached to the compute role and resource-based policies attached directly to target services like S3 or Lambda. I'll leave you with one final stark warning. Never use the wildcard star for your actions or resources just to make a permissions error go away. You aren't just fixing a bug. You're handing the keys to your entire AWS account to a piece of code that could accidentally destroy your business. So, looking at your own AWS environment today, how many wildcards are hiding in your policies right now, just waiting to be exploited? Welcome to the explainer. Let's just jump right in. Imagine you're building a mobile app, and this app needs to do something incredibly common, like uploading user photos directly to an Amazon S3 bucket. A fundamental question pops up right away. How does the app actually log in to AWS? Well, if your very first instinct is to grab an IAM user's permanent access key and hardcode it right into the mobile code, you are walking straight into a massive trap.
Seriously. Because a hacker will simply reverse engineer your app, rip out that permanent key, and potentially hold your entire cloud account for ransom.
So how do modern, highly secure applications actually log in? Well, the reality is they bypass traditional passwords entirely. Instead of relying on static, permanent keys that can be stolen once and abused forever, modern cloud architectures rely completely on temporary, self-destructing credentials.
And this brings us to a brilliantly simple core mechanism of cloud security. Now, when a human logs into an AWS console, sure, they use a password or maybe a biometric login. But when an application, a server, or a CI/CD pipeline needs to talk to AWS programmatically, it uses something totally different. Behind the scenes, it relies on the AWS Security Token Service, which we usually just call STS. Let me show you exactly how this dynamic authentication works.
To really wrap your head around STS, think about it like this. Imagine you're visiting a highly secure government building. When you arrive at the front door, they absolutely do not just hand you the master key to the building. That would be insane. Instead, you walk up to the front desk and you show your ID. After verifying exactly who you are, they print you a temporary visitor badge. Now, this badge has strict limits. It might only work for the third floor, and at exactly 5 p.m., the barcode on that badge automatically deactivates. Even if you walk outside and drop that badge right on the street, it is completely useless to whoever picks it up.
That secure visitor badge process, that is exactly what STS does for your cloud applications. STS essentially acts as that front desk security guard. It issues short-lived security credentials that are generated dynamically right on the fly. And even more importantly, they automatically expire the second their time is up. Let's break down the exact step-by-step execution flow of how your application requests and receives that temporary badge. First, your application makes an API call to STS using a very specific command called assume role. Basically, the application raises its hand and says, hey, here is who I am, and I want to temporarily assume the specific I am role to do my job. Next, STS checks to verify if the application is actually authorized to wear that hat. Finally, if it is approved, STS hands back a temporary credential package. But this is where you really need to pay close attention, because this is not your standard login package. STS gives you exactly 3 things: an access key ID, a secret access key, and a session token. To make any successful API call to AWS going forward, your application absolutely must pass all 3 of these strings together. Think about that for a second, because these credentials have a strict built-in expiration time, which can be anywhere from just 15 minutes up to 12 hours. You completely eliminate the nightmare of secret rotation. You don't have to write and maintain complex, fragile scripts just to cycle out old passwords. The system inherently cleans up after itself. Now, what's really fascinating here is how STS acts as the ultimate bridge between entirely different systems. Because once you understand that STS issues temporary trust, a whole world of secure architecture suddenly opens up to you. Let's look at a real-world deployment pipeline to see this in action. Say you're using GitHub Actions to deploy infrastructure to AWS. The old, incredibly dangerous way to do this was to create an IAM user, generate a permanent access key, and save that key permanently inside GitHub as a secret. If GitHub ever gets compromised, or say a developer accidentally exposes that secret, your entire AWS account gets hacked. But the modern secure way, that involves configuring GitHub to request temporary credentials from STS dynamically. Your pipeline gets exactly what it needs for that brief 5-minute deployment, and then the keys just vanish into thin air. Or consider federated login for a massive enterprise. If your company uses Microsoft Active Directory, your employees do not need separate AWS passwords. They simply log into their standard corporate portal. Behind the scenes, their identity provider talks to STS, and STS essentially trades their verified corporate login for an AWS session token. It's totally seamless, passwordless access. And this exact same concept brilliantly handles cross-account access. Let's say your monitoring app in account A needs to read some critical logs located over in account B. You do not copy passwords or duplicate permanent keys across those accounts. Instead, you simply grant the app in account A the permission to execute an assume role API call against a specific, highly restricted role in account B. But this is where people mess up. And honestly, it happens all the time. In fact, this is a massive trap designed specifically to catch you off guard on the AWS Certified Developer, or DVA-C02 exam. Developers will test their code locally on their laptops using their own long-term IAM user credentials. And locally, it works perfectly.
But then, they push that exact same code up to a Lambda function or an EC2 instance that relies on STS, and suddenly the application crashes. Every single API call fails with a really frustrating authentication error. So why does this happen? Well, because when they wrote their custom API requests locally, they only passed the access key and the secret key. They completely forgot the third piece of the puzzle, the session token. Remember, when you use STS, the session token is absolutely mandatory. Without it, AWS instantly rejects the request. There's also another major hurdle you need to watch out for, and that is the permissions trap. The absolutely crucial point here is understanding how your identity shifts. Imagine your application already has a set of basic permissions. You write code to call assume roles so the app can briefly access a highly restricted database. A lot of developers think their app now has its original baseline permissions, plus the new database permissions. That is entirely wrong. When you assume a role, you completely drop your original identity. You do not add permissions, you replace them. Your app can now only do exactly what that new temporary role explicitly allows and absolutely nothing else. All right, let's lock this down before we finish. Here are the 3 rapid takeaways you absolutely need to remember. Number 1, modern AWS applications authenticate using the security token service to generate temporary, automatically expiring credentials. Number 2, temporary credentials always consist of an access key, a secret key, and a strictly required session token. And number 3, the assume role API call is the primary mechanism for granting secure, cross-account, or federated access, all without ever hard-coding permanent keys. Which brings us to our final slide, and a very important warning. Never try to build your own custom credential caching and rotation logic in your application code. It is dangerous and, quite frankly, unnecessary. If you're using the official AWS SDKs, they automatically handle the STS requests. They seamlessly attach the session tokens to every single call, and they silently refresh those credentials behind the scenes right before they expire. So let the SDK do the heavy lifting. Which leaves us with one final thought to consider as we wrap up this explainer. If your current cloud infrastructure still relies on static passwords or permanent access keys just sitting in a configuration file, how many ticking time bombs are currently hiding in your code? Let's jump right into this. Picture this scenario. You've just built the next viral mobile app. It's an absolutely brilliant idea, and users are pouring in by the thousands. But right out of the gate, they want to do things like create accounts, reset forgotten passwords, and log in with their existing Google or Apple IDs. Now, if you try to build this custom authentication system completely from scratch, you're going to spend months just writing boilerplate code. And here is the truly terrifying reality. One tiny bug in that custom code will leak 1 million passwords directly onto the dark web. Just let that sink in. Think about the catastrophic failure, the agonizing downtime, the total loss of user trust, and the massive hit to your revenue. Building off from scratch is a huge emotional and financial risk. So let's talk about how to actually handle user authentication securely. The secret here? You literally don't build it yourself. Instead, you use Amazon Cognito. This is the ultimate solution. It's a fully managed service that handles user authentication and authorization for your applications. It lets you add users sign up, sign in, and robust access control to your web and mobile apps quickly and seamlessly. It completely prevents you from having to build and maintain it yourself, handling exactly one massive headache perfectly. Now, to truly understand Cognito and use it effectively, you have to split it into 2 completely separate halves. On one side, we have Cognito user pools, and on the other, Cognito identity pools. Keeping these 2 halves completely separate in your mind, that is the absolute structural foundation for everything we're going to explore in this explainer today. So let's start with the front door, the user pool. Think of Cognito user pools as your actual user directories. They're used to manage sign-up and sign-in functionality for your mobile and web apps. When a user opens your app for the very first time and creates an account, they are interacting directly with the user pool. It handles all the heavy lifting. It lets users sign up and sign in using an email, a phone number, or a custom username. And it even natively supports SMS-based multi-factor authentication. But one of the most powerful features here is its role as a federated identity broker. Let's be honest, users absolutely hate creating new passwords. They just want to use the accounts they already have. And Cognito acts as this middleman, this broker. Your users can sign in directly through a third-party social provider like Facebook, Amazon, Apple, or Google. Your app just talks to Cognito, and Cognito handles that incredibly messy, complex handshake with the social provider totally behind the scenes. So when a user successfully logs in through that front door, what do they actually get?
Well, after successfully authenticating a user, Amazon Cognito issues JSON Web Tokens, commonly called JWTs. You can think of this token as their digital passport. It is cryptographic proof that establishes exactly who the user is.
But listen close, because this is where people mess up. A user pool only proves who the user is. It does absolutely not give them permission to actually touch your backend AWS infrastructure. I really want to repeat that because it is vital to your architecture. A user pool proves identity. It does not prove what they are allowed to touch.
Let's look at how this builds into a real-world problem. Imagine your user wants to upload a profile picture from their phone directly into your private Amazon S3 bucket. If they just walk up and hand S3 their JWT token, that digital passport we just talked about, S3 is going to completely reject it. Why? Because S3 doesn't understand JWTs. S3 only understands native AWS credentials.
And this is exactly why Cognito identity pools exist. They are the precise rescue mechanism you need for the scenario. Identity pools enable you to create unique identities for your users and authenticate them with identity providers. Once you have that identity, the identity pool allows you to obtain temporary, limited privilege AWS credentials so your app can actually access other AWS services safely. Let's walk through this exact architectural flow step by step. Step 1. Your mobile application gets that JWT token from the user pool after a successful login. Step 2. It walks over to the identity pool and essentially says, hey, here's cryptographic proof of who my user is. Step 3. The identity pool verifies that token and hands back a temporary, strictly scoped AWS access key and secret key. Step 4, your mobile app uses those exact temporary keys to upload the photo directly to S3. Notice what just happened there? You completely bypassed the need for your backend servers by using this token exchange. Grasping this mental model is an absolute game changer. Think about it like this. The user pool is the DMV. They check your birth certificate and they issue your driver's license. The identity pool, on the other hand, is the rental car agency. They look at your license, they verify you are a real, valid person, and then they hand you the keys to an actual car. Think about that for a second. It perfectly, cleanly separates identity from capability. To make it even easier to remember for those of you already working deep in AWS, let's map this technically. You can think of user pools as being exactly like IAM users or Microsoft Active Directory. It's a directory of people. On the flip side, think of identity pools as being exactly like an IAM role. It's an entity you assume to get temporary permissions to do a specific job. Now listen closely, because if you're taking the DVA-C02 exam, this is a massive insider trap. If an exam question asks how to let users sign in, manage passwords, or get a JWT, the answer is always a user pool. But if the question asks how to grant an app user direct access to an AWS service like S3 or DynamoDB, or how to issue temporary AWS credentials, the answer is an identity pool. Do not fall for that trap. Once you fully understand this, identity pools give your architecture absolute superpowers. You can write an IAM policy and attach it directly to the identity pool, restricting exactly what that specific user can do. Your mobile app can scale securely to millions of users seamlessly. Everyone uploads their files directly to AWS, nobody can touch anyone else's data, and the absolute best part, your custom backend compute does absolutely zero work. Identity pools even support unauthenticated guest users. That means you can give temporary credentials just to let someone browse a public catalog before they ever decide to create an account. All right, let's lock this down. Here are your 3 rapid-fire takeaways for today. Number 1. Cognito user pools act as your front door user directory, handling signups, social logins, and issuing those JWT passports. Number 2, Cognito identity pools exchange those JWT tokens for temporary AWS credentials so your application can securely touch backend resources. Number 3, you must combine both pools to build a highly scalable, secure architecture where users interact directly with AWS resources, entirely skipping the bottleneck of routing traffic through a backend server. Which brings us to one final warning, and really the most important question for you to take away. Will you remember to keep the 2 pools straight so your application stays completely secure in production? Seriously, never confuse the 2. Users sign in to the user pool, users get AWS access from the identity pool. Keep them straight, and your serverless architecture is going to be bulletproof. Okay, let's dive right into this. Welcome to another explainer. Today, we are focusing on something absolutely crucial: securing cloud applications with AWS Secrets Management. Imagine this. You just finished building a massive new feature, right? You push the code to GitHub. 20 minutes later, an automated bot scrapes your repo, finds your production database password, and permanently deletes your entire customer database. Now, why did that happen? Well, because you hard-coded your secrets and you really didn't understand where AWS applications should actually store them. So let me show you how to securely manage your application configurations. Every single application needs secrets to function. We are talking about database passwords, third-party API keys, and authentication tokens. But here is the fatal mistake developers make: treating these secrets like standard code and dropping them directly into their configuration files or environment variables. Listen, here is the golden rule. An application should never permanently hold a secret. It should retrieve it on the fly. Think about it like this. You wouldn't tape the combination of a bank vault right onto the front door, would you? Of course not. You would lock it inside a secure manager's office, and the bank teller would have to literally walk over and ask for it every single time they needed to open the vault. Well, in AWS, you actually have two secure offices to choose from for this: AWS Systems Manager Parameter Store and AWS Secrets Manager. Let's look at Systems Manager Parameter Store first. Parameter Store is your simple, highly effective configuration storage. It lets you organize your data into clean, logical hierarchies. So you can create a path like /production, /frontend, /API key, store the key as an encrypted, secure string, and then your code can just fetch it using the AWS SDK. It is incredibly cost-effective. Actually, standard parameters are completely free. But it is just a locker. It strictly holds exactly what you put into it. Now, here is where this gets really interesting. Enter AWS Secrets Manager. Secrets Manager is built specifically for high-value secrets. While Parameter Store just holds your password, Secrets Manager actively manages it. It features native automatic secret rotation, plus it integrates directly with AWS databases like Amazon RDS, Amazon Aurora, and Amazon Document DB. Now imagine this. Your company's security policy dictates that production database passwords absolutely must be changed every 30 days. If you use Parameter Store, you have to manually generate a new password, update the database engine, update the Parameter Store record, and pretty much pray you didn't cause any downtime. But with Secrets Manager, you simply configure a rotation schedule. Every 30 days, Secrets Manager triggers an AWS Lambda function in the background. That Lambda function securely connects to your RDS database, generates a brand new complex password, updates the database, and stores the new password. And the best part? Your main application never even notices the downtime because it always asks Secrets Manager for the latest password dynamically. So how do you actually implement this as an AWS developer? Well, if you have an AWS Lambda function that needs to talk to a database, you write a few lines of code using the AWS SDK, like Boto3 for Python. When the function executes, it makes an API call to Secrets Manager using getSecretValue. Secrets Manager then decrypts the payload and hands it directly to your Lambda function right in memory. Or if you are running containers on Amazon Elastic Container Service, or ECS, you don't even have to write the API call in your code at all. You just map the secret ARN directly inside your ECS task definition. When the container spins up, ECS automatically fetches the API key from Secrets Manager or Parameter Store and safely injects it into the container's environment variables before your code even starts running. Now, this is where people mess up, and it is exactly how AWS will trap you on the DVA-C02 exam. You write the exact code to fetch the secret, you deploy the Lambda function, but your code immediately throws an access denied error. Why? Well, because you forgot that AWS is completely locked down by default. Just because your Lambda function and your secret are sitting in the exact same AWS account, that absolutely does not mean they are allowed to talk to each other. You must explicitly grant your compute resource permission to retrieve that secret. You have to attach an IAM policy to your Lambda execution role or your ECS task role that explicitly allows the Secrets Manager getSecretValue action for that specific secret ARN. Without that exact IAM permission in place, your application is completely blocked. Think about that for a second. You are decoupling the password from the code, and you are entirely controlling access using IAM. If a junior developer downloads the source code to their local laptop, they literally cannot connect to the production database because their local IAM user doesn't have the permissions to read the secret, even though the code is identical. That is true cloud security. All right, let's lock this down. 3 rapid takeaways. Number 1, Never hardcode database passwords, API keys, or tokens in your source code. Your applications must fetch them dynamically at runtime. Number 2, use Systems Manager Parameter Store for hierarchical, low-cost configuration data, but use Secrets Manager when you need automatic credential rotation for databases. And number 3, your compute resources like Lambda and ECS must have explicit IAM permissions attached to their execution roles to successfully retrieve the secrets. Okay, one final warning before we wrap up. When you call the Secrets Manager API, you pay for every single request. So if you have a high-traffic application, please do not make an API call for every single user request. You need to use the official AWS client-side caching library in your code. It caches the secret in memory for a few minutes so you don't completely bankrupt your company making thousands of identical API calls per second. Now, doesn't that completely change how you approach application architecture? Picture this. A hacker breaches your AWS account, downloads a 50-gigabyte backup of your Amazon RDS database, and opens it right up on their laptop. But instead of seeing your users' passwords and credit cards, they just see a massive wall of scrambled, completely random characters. They got the data, sure, but that data is completely useless. So why is that? Well, it's because you encrypted it. And more importantly, it's because you understood exactly how AWS actually manages the keys. Let's dive into how AWS encryption actually works behind the scenes. Out there in the cloud, your data really exists in one of two states. You've got your plain text, which is just your normal readable data, and then you have your ciphertext, which is the scrambled, totally unreadable result after encryption happens. Now, to turn that plain text into ciphertext, you're going to need a cryptographic key. And in AWS, you manage those keys using the AWS Key Management Service, or KMS for short. But listen, here is the absolute most important mental model you've got to adopt, especially if you're taking the DVA-C02 exam. AWS KMS does not manage your data, it strictly manages your keys. Think about it like this. Imagine you have a highly secure bank vault. Now, the vault holds the money, but the bank manager holds the physical key. If a bank robber manages to steal the entire steel vault and takes it home, it doesn't even matter. Without the manager's key, they literally can't open it. In the AWS world, your services like S3, EBS, and RDS, those are your vault. KMS is the bank manager. Now, here is where this gets really interesting. How does AWS actually encrypt a massive, let's say, 10-gigabyte video file in an S3 bucket? Well, it absolutely does not send that 10-gigabyte file over the network to KMS. You see, KMS has a hard physical limit. A KMS key can only encrypt up to 4 kilobytes of data directly. Not gigabytes, kilobytes. So instead, AWS uses this brilliant architecture called envelope encryption. So when you upload that massive video to S3, S3 makes a really quick API call over to KMS. It basically asks KMS to generate a brand new, completely unique symmetric data encryption key, or DEK. KMS creates that data key, uses your master KMS key to encrypt a copy of it, and then it hands both the plaintext data key and the encrypted data key right back to S3. From there, S3 uses that plaintext data key to quickly lock up your video file right there on the local storage server. Then, and honestly, this is the genius part, it permanently deletes the plaintext key from memory, and it just saves the encrypted data key right next to your newly encrypted video file. To read the video later on, S3 just sends that encrypted data key back to KMS to be unlocked. The result of all this? You get massive performance, because all the heavy lifting happens locally on S3. And you get massive security, because your master key never, ever leaves KMS. Now, this whole process protects your data at rest, meaning when it's just sitting there on a physical hard drive in an AWS data center. But what about when that data is actively traveling across the internet? Well, that is encryption in transit, and you protect that using SSL or TLS certificates. Basically, data in transit prevents someone from intercepting your network traffic, while data at rest prevents someone from walking out the door with your physical hard drives. Okay, so now you have to choose who actually controls your KMS master keys. AWS gives you two main options here: AWS managed keys and customer managed keys. And honestly, this is where people mess up. They choose customer managed keys for absolutely everything, thinking it's just the default. But customer managed keys cost $1 per month per key, plus API usage fees. If you have hundreds of keys in your account, your monthly bill is going to explode. On the flip side, an AWS managed key is completely free. AWS automatically creates it for you the very first time you encrypt something like an EBS volume or an RDS database. AWS manages the key rotation for you, and AWS manages the permissions. It's really the free, hands-off, easy solution.
So why would you ever choose to pay for a customer-managed key? One word: control. With a customer-managed key, you get to write the strict IAM policies that determine exactly who can and cannot use the key. You also get to manually rotate the cryptographic material. If you're building a highly regulated application, or let's say you need to share an encrypted snapshot across 2 totally different AWS accounts, you absolutely must use a customer-managed key. Why? Because AWS managed keys simply cannot be shared across accounts.
Now, I want you to imagine this scenario. You're writing an AWS Lambda function, and you pass a third-party API key into the function using an environment variable. Your code runs perfectly. Great. But later on, a junior developer logs into the AWS console, clicks on your Lambda function, and just casually looks at the configuration tab. That API key is sitting right there in plain text. They copy it, and suddenly your third-party account is completely compromised. To implement this correctly as an AWS developer, you absolutely must encrypt your Lambda environment variables using KMS. You just configure Lambda to use a KMS key to encrypt those variables at rest. Then when your code actually executes, AWS seamlessly decrypts the variables and injects them right into the runtime environment behind the scenes. Your SDK never even handles the KMS API calls, but any human eyes looking at the AWS console, they're only going to see that scrambled ciphertext. Also, you really need to watch out for the key rotation trap on the exam. If you enable automatic key rotation on a customer-managed key, KMS is going to generate new cryptographic material every single year. But developers often panic when they hear this. They think, wait, if the key changes, how do I decrypt data I saved 3 years ago? I mean, think about that for a second. If AWS just threw away the old key, your entire database would be permanently destroyed. But don't worry, they thought of that. AWS KMS securely preserves all previous iterations of the cryptographic material. Until you explicitly and manually delete that KMS key, AWS does not remove any of the rotated key material. So when a request comes in to decrypt a really old file, KMS automatically recognizes exactly which version of the key was originally used, and it decrypts it flawlessly. You will never lose access to your old data. All right, let's lock this down. Here are 3 rapid takeaways you need to remember. Number 1, KMS does not encrypt your massive files directly. Instead, it uses envelope encryption to generate data encryption keys that lock your data locally on the storage service itself. Number 2, AWS managed keys are totally free, but they lack cross-account sharing. Meanwhile, customer managed keys cost money, but they give you absolute control over access policies and rotation. And number 3, you must actively encrypt your Lambda environment variables with KMS to prevent sensitive data from being exposed in plain text right there in the AWS console. I'll leave you with one final warning. Never delete a customer-managed KMS key unless you are absolutely 100% sure that no data is currently encrypted with it. Because if you delete that master key, every single file, every database, and every snapshot tied to it instantly turns into permanent, completely unrecoverable ciphertext forever. So before you ever hit that delete button, ask yourself, do you know exactly what that key is guarding? And what other invisible security traps are lurking in your cloud architecture right now, just waiting to be tripped? Picture this. You spend hours writing the absolute perfect Python script. It runs flawlessly on your laptop, right? You zip it up, deploy to AWS Lambda, click test, and instantly you get hit with a massive red error. Runtime import module error. Just like that, your deployment is completely broken. So why does this happen? Well, it's usually because you treated a Lambda deployment like a simple file upload. In this explainer, we're going to look at exactly why your Lambda deployments keep breaking, and more importantly, how to actually package your code for production. You see, to AWS, your code is literally just a text file. Lambda doesn't magically know how to run it. You have to hand AWS a perfectly structured box. And that box? That's your deployment package. This package strictly defines exactly what Lambda is going to execute. If that box is packed wrong, the function crashes. Now, you have exactly 2 ways to pack this box. You can use a zip archive or a container image. Let's start with the zip deployment. When you're writing code locally, you're installing libraries, right? Things like requests for Python or Axios for Node.js, but those libraries live hidden away in your local machine's folders. If you just select your index.js file, right-click, hit compress, and deploy that zip straight to Lambda, your code is going to fail. Think about that for a second. Lambda is a completely blank slate. It does not have your local libraries. You absolutely must package all your dependencies inside that zip file, right next to your code. But here's the kicker. Even if you do that, you can still trigger a massive deployment failure. Now, imagine this. You package your dependencies perfectly on your Windows or Mac laptop. You deploy it to Lambda, and it still crashes. Why? Because of a local versus cloud mismatch. You see, your local machine compiled those dependencies for a Mac or Windows operating system, but AWS Lambda, it runs on Amazon Linux. If your code uses libraries with compiled C bindings, think NumPy or Pandas, you are going to have a runtime compatibility failure. You absolutely must compile that deployment package in a Linux environment before ever deploying it to AWS. Okay, next up, we need to understand the upload methods, because AWS will literally block your deployment if you don't know the rules here. If your zip file is under 50 megabytes, you're good to upload it directly through the AWS console or the AWS CLI. But if your zip file is over 50 megabytes, that direct API call is going to reject it. You have to upload the zip to an Amazon S3 bucket first, and then point Lambda to that S3 URL. Oh, and watch out for the absolute ultimate size limit. Your total unzipped deployment package cannot exceed 250 megabytes. If it's 251 megabytes, Lambda permanently blocks the deployment. No way around it. So what do you actually do if your dependencies are massive? You use a Lambda layer. A layer is essentially a separate zip archive that contains all your heavy libraries or custom runtimes. The beauty is, you upload the layer once, and then you can just attach it to multiple functions. Think of it kind of like moving to a new apartment. Your application code is like your suitcase of clothes. It's light, it changes often, and it's super easy to carry. Your dependencies, on the other hand, are the furniture. Heavy and rarely changes. You obviously don't want to carry a sofa every time you travel, right? Layers basically let you leave that heavy furniture right there in the apartment, so you only ever have to upload your lightweight code. But wait, what if your application is, say, 5 gigabytes, and you absolutely need these massive machine learning models? In that case, you abandon the zip file entirely, and you use a container image deployment. Lambda actually allows you to package your code and dependencies as a Docker container image, all the way up to 10 gigabytes in size. You push that image to Amazon Elastic Container Registry, or ECR, and then deploy it to Lambda. But here is the absolutely critical execution detail. You cannot just take an arbitrary web server container and run it. The container must implement the Lambda Runtime API. If it doesn't do that, Lambda has literally no way to pass HTTP events into your container, and the deployment is going to fail. Now, this is where people really mess up. Imagine you deployed the perfect zip file. All the dependencies are there, it was perfectly compiled on Linux, and you still get an error saying handler not found. So what gives? Well, the handler is the exact entry point where AWS Lambda actually begins executing your code. In your Lambda configuration, the handler is defined as a string. Usually it's something like index.handler or app.lambda_handler. The first part of that string is the exact name of your file without the extension. The second part is the name of the actual function inside that file. So, for example, if your file is named main.py and your function is called start_process, but your Lambda configuration is looking for index.handler, Lambda is just blindly searching for a file called index that doesn't even exist. It crashes instantly. You absolutely must ensure that the handler string in the AWS console matches your deployment package structure exactly. Okay, let's lock this down. Here are 3 rapid takeaways for us. Number 1, your deployment package has to contain your code and all dependencies compiled specifically for Amazon Linux, or your function will crash due to missing or incompatible modules. Number 2, zip deployments are strictly limited to 250 megabytes unzipped, and anything over 50 megabytes must be uploaded via Amazon S3. For larger workloads, up to 10 gigabytes, you've got to use container images stored in ECR. And number 3, Lambda layers solve deployment limits by separating those heavy dependencies from your application code, while the handler configuration tells Lambda exactly which file and method to execute. Before we wrap up this explainer, I have one final warning for you. Changing your deployment package completely overwrites the code. You should always map your API gateway triggers to specific Lambda versions or aliases. Because if you just deploy directly over the latest version, a single broken deployment package will instantly take down your entire production system. So, is your next deployment going to be a perfectly packed box or a ticking time bomb?
You push a quick bug fix to production on a Friday afternoon. You drag and drop the files manually onto your servers. 10 minutes later, your entire application crashes. Users are getting 500 errors, and you are scrambling to figure out which file broke the system. Why? Because you relied on manual human deployment, and humans make mistakes. Let me show you what actually happens when you push code to AWS using a proper CI/CD pipeline and how it automates your deployments safely.
Think about it like this. A CI/CD pipeline is an automated factory assembly line for your code. Continuous integration is the quality control checker. It automatically builds and tests your code every single time you push an update. Continuous delivery is the delivery truck. It automatically takes that tested code and safely releases it to your infrastructure without you lifting a finger.
The automated journey happens in 3 steps: source, build, and deploy. It kicks off with the source stage. You commit your code and push it to a repository, like GitHub or AWS Code Commit. The moment your code hits that repository, AWS Code Pipeline detects the change and triggers the entire workflow automatically.
Toad Pipeline immediately hands the code over to the build stage. This is powered by AWS Code Build. Code Build spins up a temporary pre-configured compute environment in the background. It pulls down your raw source code and looks inside for a very specific file to tell it what to do.
This is where people mess up. They configure code build, but the build instantly fails. Why? Because they put their build instructions in a subfolder. For AWS Code Build to work, you absolutely must have a file named buildspec.yml located at the exact root of your source code repository. If it is anywhere else, Code Build panics and crashes. Code Build reads that buildspec.yml file, installs your dependencies, runs your automated unit tests, and compiles the final software. But how does the compiled software actually get to the deployment servers?
Through artifacts. When Code Build finishes, it packages your compiled application into a file called an artifact. It does not hand this directly to the deployment server. Instead, it securely uploads that artifact into an Amazon S3 bucket. Think about that for a second. Your pipeline stages are completely decoupled. Code Pipeline acts as the invisible coordinator, taking the compiled artifact from the S3 bucket and passing it down the line to the next stage.
Now here's where this gets interesting. You don't always want code to go straight to production just because it passed an automated test. You need a human checkpoint. In Code Pipeline, you can easily add a manual approval stage. When the pipeline reaches this stage, it completely pauses execution. It triggers an AWS CloudWatch event, which fires an Amazon SNS notification directly to your QA manager's email or Slack channel. The code sits frozen. Only when a manager clicks approve does Code Pipeline grab the artifact from Amazon S3 and move it to the final deploy stage.
In the deploy stage, a service like AWS Code Deploy takes over. Just like Code Build needed a build spec file, Code Deploy looks for an appspec.yaml file to understand exactly how to safely install your application onto your Amazon EC2 instances or Lambda functions.
Now imagine this. The deployment goes through, but the new code contains a hidden memory leak that starts crashing your EC2 servers one by one. If you deployed manually, your business would be down until you figured out how to revert the changes. But because you are using Code Deploy, you are safe. Code Deploy supports automatic rollbacks. If it detects that your deployment failed, or if you configure it to watch an AWS CloudWatch alarm that suddenly triggers because your CPU spiked to 100%, Code Deploy will automatically halt the deployment and instantly roll your servers back to the last known stable version of your application. Your users experience zero downtime, and your application self-heals.
Let's lock this down. 3 rapid takeaways for the DVA-C02 exam and production. 1. Code Pipeline automates the release process, moving code sequentially through source, build, and deploy stages using Amazon S3 to store and pass artifacts. 2. AWS Code Build requires a buildspec.yaml file placed strictly at the root of your repository to execute build commands and run your automated tests. 3. You enforce production safety by adding manual approval stages that notify teams via Amazon SNS, and by configuring Code Deploy to trigger automatic rollbacks if CloudWatch alarms go off.
One final warning. Never skip the testing phase in your buildspec.yaml file just to make your pipeline run faster. A CI/CD pipeline that doesn't run automated tests isn't a safety net. It is just a highly efficient machine for deploying broken code into production. So, how confident are you in what your pipeline is deploying today?
Picture this. You just pushed your code to GitHub. 5 minutes later, your team lead messages you. The deployment pipeline is blocked. Your AWS Code Build stage just threw a massive red failed status, and suddenly production is completely stalled.
Section 1. The production build failure.
So why did this happen?
Well, it's usually because you didn't understand how AWS actually compiles your code. You're treating the build process like a magic black box. But let me show you exactly why your build suddenly failed. The absolute core mental model you must understand for the exam is this: build systems create deployable artifacts.
Section 2. The pop-up kitchen analogy. AWS Code Build is essentially a fully managed temporary factory. Think about it like a pop-up kitchen. A chef, which in this case is Code Build, walks into a totally empty room and builds a fully functioning kitchen. That kitchen is your temporary Docker container build environment. They cook exactly one meal using a highly specific recipe. They put the meal in a to-go box, that's your deployable artifact, and then they completely demolish the kitchen.
But wait, how does the chef actually know what to cook? Well, that recipe is a file called the buildspec.yaml.
Section 3. The 4 build spec phases. This YAML file tells the temporary container exactly what commands to run, and it's strictly divided into 4 distinct phases. First up, we have the install phase. This is where you download your dependencies. Think running npm install for Node.js or pip install for Python. Second is the pre-build phase. You execute your final setup commands right here. Things like logging in to the Amazon Elastic Container Registry, or ECR, so you're authenticated and perfectly ready for a Docker build.
Third is the build phase. This is where the heavy lifting actually happens. Your code compiles, your Docker images are built, and your automated unit tests execute. Finally, we reach the post-build phase. Here, you add the finishing touches. You might zip up the output files or push your newly built Docker image directly to the registry.
Section 4. Security and folder traps.
Now listen closely, because this is where people mess up, and it's a guaranteed trap on the exam. Developers will write a beautiful, perfect buildspec.yaml file, but they place it inside a subfolder, like /config, and boom, the pipeline instantly fails. Why? Because AWS Code Build strictly requires the buildspec.yaml file to be located at the absolute root of your source code repository by default. Think about it. If the chef can't find the recipe right on the front counter, the kitchen just shuts down.
Now, here's where this gets really interesting. Let's say your build needs to securely access a database password to run an integration test during that build phase. If you hardcode that password directly in your build spec file, it gets saved right into your Git repository. It gets logged in plain text. You just created a massive security breach.
To fix this, Code Build allows you to define environment variables directly in the build spec. Sure, you can define plain text variables for basic settings, but for sensitive data, you absolutely need to reference the AWS Systems Manager parameter store. Code Build will securely pull the secret at runtime and inject it safely into the temporary container's environment variables. Problem solved.
Section 5. Troubleshooting failed cloud builds.
Now imagine this. Your build fails right in the middle of the build phase. But remember our pop-up kitchen analogy? The container destroys itself the moment the build finishes or fails. The evidence is just gone. So how do you figure out what broke? Well, Code Build automatically streams every single line of console output directly to Amazon CloudWatch logs. You can even set up CloudWatch alarms to trigger Amazon Simple Notification Service, or SNS, notifications the exact second a build fails.
But let's be real, staring at CloudWatch logs can be slow. What if you have a really complex Docker build that just keeps failing, and you don't want to wait 5 minutes for the cloud pipeline to spin up every single time you change one line of code?
That's when you use the Code Build local build agent. You can actually run Code Build locally on your own computer using Docker. This perfectly simulates the exact AWS cloud environment, allowing you to deeply troubleshoot, run your test stages, and debug your code without pushing a single commit to AWS. Think about that for a second. You get the exact cloud environment running directly on your laptop to guarantee the build will succeed before it ever even touches the pipeline. Once your build actually does succeed, the final step is artifact generation. In the artifacts section of your build spec, you define exactly which files and folders Code Build should keep. Code Build takes those specific files, zips them up, encrypts them using the AWS Key Management Service, or KMS, and uploads that single deployable artifact directly into an Amazon S3 bucket. At that exact moment, Code Build's job is officially done, and the deployment service takes over.
Section 6. 3 rapid takeaways. Let's lock this down.
Takeaway number 1. AWS Code Build uses temporary container environments to install dependencies, run tests, and generate a final deployable artifact. Takeaway number 2. Your instructions absolutely must be defined in a buildspec.yaml file located at the exact root of your repository, or the build will immediately fail. And takeaway number 3. When builds fail, you troubleshoot by reviewing the output in Amazon CloudWatch logs or by running the code build agent locally using Docker to simulate the cloud environment.
I want to leave you with one final warning. Never skip your test stages inside code build just to make the pipeline run faster. Code build is your ultimate quality control checkpoint. If you bypass the tests, you aren't optimizing your workflow, you are just automating the delivery of broken code into production. So take a look at your pipelines today. What hidden traps are lurking in your build spec right now?
Welcome to this explainer. Today, we're diving into architecting infrastructure. Specifically, we're going to break down the AWS CloudFormation blueprint. Let's jump right in.
Picture this scenario. A junior developer accidentally deletes your production database subnet. System offline.
Your CEO runs in visibly panicked and asks, "How long until we are back up?" Now really think about your answer here.
If you built your system by manually clicking around the AWS console, the answer is days. You'd have to remember exactly how every single security group, routing table, and gateway was manually wired together. But if you used AWS CloudFormation, you just press enter and your entire infrastructure rebuilds itself flawlessly in exactly 5 minutes.
So, the core mental model you absolutely need to grasp, especially for the exam, is pretty simple. Infrastructure can and honestly must be deployed exactly like software. You do not treat servers, load balancers, and databases as physical hardware anymore. Instead, you treat them as lines of text in a JSON or YAML file. This right here is what we call infrastructure as code, or IAC for short.
To actually use AWS CloudFormation, you're going to create a text file, which is called a template. Think about it like this. The template is basically the architectural blueprint for a house. It defines exactly where the walls go, where the plumbing is, and how many windows you have. But as we all know, a blueprint is just paper, right? It isn't an actual house. When you hand that JSON or YAML blueprint over to AWS, CloudFormation acts as your construction crew. It reads the code and physically builds the environment. And in the AWS world, that finished deployed environment is called a stack.
Now, inside your template, the only mandatory section you absolutely must write is the resources block. This is where you declare exactly what you want, like say an Amazon EC2 instance or an S3 bucket. But here's the kicker. You do not write complex scripts. You don't write the underlying API calls. You simply declare your desired end state, and CloudFormation figures out exactly how to make it happen for you.
Think about that for a second. You don't have to write custom code to check if a VPC exists and then wait for it to be ready and then attach an internet gateway. CloudFormation inherently understands dependency ordering. It mathematically maps out your resources, realizes the VPC has to exist before the subnets, and builds them all in the absolute perfect sequence automatically. It's really that smart.
Now, imagine this. Let's say you need a development environment, a staging environment, and a highly available production environment. So do you go and write 3 separate, massive YAML templates? Absolutely not. You write one single template and you use the parameters section. Parameters allow you to inject dynamic values into your template right at the exact moment you hit deploy. So you pass the value t2.micro for the dev stage and m5.large for the production stage. Just like that, you have one repeatable code base creating infinite, perfectly identical environments.
And when that stack finishes building, you use the output section to export data, like the ID of your brand new VPC. Why? So that a completely separate CloudFormation stack can read that exact ID and deploy its own resources securely inside it. It connects everything seamlessly.
Now here's where this gets really interesting. What happens when your deployment actually fails? Let's say you deploy a stack. It creates 10 resources perfectly, but then the 11th resource fails because you hit some AWS account limit. Does AWS just leave your account littered with half-built, broken infrastructure?
No, definitely not. CloudFormation triggers what's called an automatic rollback. The very moment a failure occurs, CloudFormation reverses direction. It systematically deletes the 10 resources it just created, safely returning your AWS environment to its exact previous state. It is a strict all-or-nothing deployment, meaning you never have to go in and manually clean up broken resources.
But listen closely, because this is where people mess up. And honestly, it is how you will destroy a production database if you aren't careful. Let's say you have a running stack. and you need to update the storage size of an EC2 instance. Well, if you just blindly edit your YAML file and push the update, CloudFormation might completely delete the old instance and recreate a brand new one from scratch just to apply that change. Doing that would wipe out all of your data in the process.
To prevent this massive headache, as an AWS developer, you absolutely must use change sets. A change set is essentially a preview. It analyzes your newly updated template against the currently running stack and gives you a highly detailed report of the exact blast radius. It explicitly warns you, literally saying, if you execute this deployment, I will modify these two resources and I will permanently replace this specific database. You review that change set, verify it's completely safe, and only then do you actually execute the deployment.
Now, watch out for the ultimate production trap on the exam. You've deployed your perfect infrastructure as code. Everything is managed beautifully by CloudFormation. But at 2 a.m., a panicked engineer logs directly into the AWS Management Console and manually changes a security group rule to fix a live bug. Suddenly, your code and your reality no longer match. Your YAML file says port 80 is closed, but the live server has port 80 wide open. This nightmare scenario is called configuration drift.
To fix this, CloudFormation provides a feature called drift detection. You just click a button, and AWS instantly scans your live stack, flagging any single resource whose actual physical configuration has drifted from the expected state defined in your code. Your job then is to take that manual console fix, write it back into the YAML template, and redeploy it. That way, your code goes back to being the ultimate source of truth again.
Okay, let's lock this down with 3 rapid takeaways from this explainer. 1. CloudFormation uses declarative JSON or YAML templates to build and manage entirely repeatable environments, which we call stacks. 2. You safely update running environments by generating change sets. This lets you preview the blast radius before you apply any modifications. And 3. You use parameters to dynamically inject values for multi-environment deployments, and you use drift detection to catch any manual changes made outside of the codebase.
I want to leave you with one final warning. Never manually delete a resource in the console if it was created by CloudFormation. If you do, the next time CloudFormation tries to update that stack, it will panic, it will fail, and you will spend hours trying to manually untangle the broken dependency graph. Always update the code. Because think about it. If your code isn't the absolute truth, are you really controlling your infrastructure, or is your infrastructure controlling you?
Picture this. It's 3 a.m. Your primary AWS region just went completely offline. Your CEO is on the phone screaming, asking exactly how long it's going to take to get the backup region running.
Now, if you built your cloud environment by manually clicking around the AWS console, well, your answer is probably going to be, I don't know, maybe tomorrow. Because now you have to try and remember exactly which buttons you clicked, which security groups you attached, and exactly how you configured those VPC subnets, 6 months ago?
But what if you used infrastructure as code? You literally just press enter and your entire production architecture perfectly rebuilds itself in 5 minutes. Let me show you why manual AWS setups always break eventually and why treating your infrastructure exactly like software is pretty much the only way to survive in production.
So the core mental model you really need to wrap your head around for the DVA-C02 exam is this: manual infrastructure creates inconsistency.
We call this manual approach ClickOps. You know the drill. You log into the AWS Management Console, you click Launch Instance, you click Create Database, and you click Create S3 Bucket. And honestly, it feels incredibly productive in the moment. But I'm telling you, ClickOps is a massive operational trap.
Think about it like this. ClickOps is basically like building a massive, complex Lego castle without an instruction manual. Sure, you might get it right the first time through trial and error, but if someone accidentally drops it and smashes it to pieces, you will absolutely never be able to build it exactly the same way again.
Now, infrastructure as code, or IAC for short, is that instruction manual. You write a template like an AWS CloudFormation or an AWS SAM YAML file that explicitly declares every single brick, every single network route, and every single permission.
All right, now imagine this scenario. You've got a development environment and a production environment. You set them both up perfectly on day one using the console.
Fast forward a month, and a developer runs into a network bug in the dev environment. To fix it quickly, they manually open port 8080 in the development security group. Boom, the bug is fixed. But they forget to tell anyone what they did. 2 weeks later, you push that exact same application code to production, and it instantly crashes.
So why? Because of environment drift.
Those two environments are no longer mathematically identical. A simple human error introduced this hidden configuration difference that literally just took down your live application.
Now, if you were using infrastructure as code, this scenario is physically impossible. To open port 8080, that developer must change the YAML code, commit it to the Git repository, and push it through a CI/CD pipeline. Your infrastructure is literally just version-controlled software.
Think about that for a second. If a bad infrastructure change takes down your application, you don't have to frantically click through the AWS console trying to hunt down the broken setting. You simply execute a git revert to the last known working commit, redeploy your template, and your environment instantly self-heals. Your entire disaster recovery strategy just becomes a simple code rollback.
Now, here's where this gets really interesting. You see, having version-controlled infrastructure isn't just about preventing outages. It's actually about operational reliability when you're scaling your team. Seriously, what happens when your company hires 5 new developers?
If you're still relying on manual setups, you basically have to hand them a 50-page Word document filled with outdated screenshots, and they're going to spend their entire first week just trying to configure a local testing environment. But if you use IAC, you just give them a single AWS SAM template. They run SAM deploy, and 10 minutes later, they have a flawless, perfectly configured exact replica of the production environment running in their own sandbox. That kind of infrastructure reproducibility is how modern engineering teams actually scale.
But listen, this is where people mess up, and I'm telling you, it is a massive trap on the DVA-C02 exam. Let's say you adopt AWS CloudFormation. You deploy your infrastructure perfectly as code.
But then, 3 months later, a live database issue causes a Severity 1 outage. In a total panic, a senior engineer logs directly into the AWS Management Console, completely bypasses the code, and manually changes an RDS parameter group just to get the site back online. You just poisoned your infrastructure. Because now, your code and your reality are fundamentally out of sync. Think about it. If you run your CloudFormation deployment tomorrow just to update a Lambda function, CloudFormation is going to look at the database, realize it doesn't match the template, and it might completely overwrite that senior engineer's manual fix, taking the entire site down all over again.
So, to fix this, AWS provides a brilliant feature called drift detection. As an AWS developer, you absolutely must actively run drift detection against your CloudFormation stacks. It basically acts as an audit, scanning your live AWS environment and explicitly flagging any resource that has been manually modified outside of the code. Once you actually find that drift, your job is to take that senior engineer's manual fix, write it back into the YAML template, and redeploy it.
Bottom line, your code must always be the ultimate source of truth.
All right, let's lock this down with 3 rapid takeaways. 1. Manual ClickOps pretty much guarantees human error and environment drift. You have to use infrastructure as code to ensure your development, staging, and production environments are absolutely identical. 2. IAC treats your servers and databases just like software, which lets you use Git version control to achieve team consistency, real infrastructure reproducibility, and instant disaster recovery. And 3. Never manually edit a resource in the console if it was originally provisioned by code. Always use CloudFormation drift detection to catch those unauthorized manual changes and immediately pull those fixes back into your templates.
I want to leave you with one final warning. If you're sitting there thinking that writing CloudFormation or SAM templates just takes way too long compared to clicking through the console, well, you're only optimizing for day 1. And hey, day 1 is easy. Day 100, when your database is corrupted, your servers are failing, and your entire team is panicking, that is when infrastructure as code is the only thing that will actually save your job.
Picture this. You've got a really simple goal. You just want to deploy a single AWS Lambda function and wire it up to an Amazon API gateway. Sounds easy enough, right? So, you open up a raw AWS CloudFormation template to write your infrastructure as code. Well, 2 hours later, you're staring at 300 lines of incredibly complex YAML. Your eyes are practically bleeding, and the worst part, the deployment still fails. Why did this happen? Simply put, because you used the exact wrong tool for the job. Let's fix that. In this explainer, I'm going to show you the absolute fastest, most efficient way to deploy serverless applications on AWS. To fix all this crazy complexity, AWS created the Serverless Application Model, which is way better known as AWS SAM. The core mental model you absolutely must understand for the DVA-C02 exam is this. AWS SAM simplifies serverless deployments. It is an open-source framework built specifically to streamline exactly how you create and manage your serverless resources. Think about it like this.
Writing raw CloudFormation, it's literally like building a house by manually mixing the cement and laying every single brick yourself by hand. But writing a SAM template, that's like ordering a modular, prefabricated house that just snaps together flawlessly in a single afternoon. See, a SAM template is essentially just a CloudFormation template, but with a massive superpower. At the very top of your YAML or JSON configuration file, you add exactly one magic line of code. Transform: AWS : serverless - 2016-10-31. Now, when you deploy, AWS reads that transform line, takes your 20 lines of super simple SAM syntax, and seamlessly expands it into the hundreds of lines of raw CloudFormation that are actually required to build the environment behind the scenes. Because of this massive shortcut, you don't have to define standard, verbose cloud resources. Instead, you define specific serverless resource types. With just a handful of lines of code, you can provision an AWS serverless function for your Lambda code, an AWS serverless API for your API gateway, and an AWS serverless simple table for your DynamoDB database. Now, here's where this gets really interesting. If you want to connect an API gateway to a Lambda function in raw CloudFormation, man, you have to manually define the API, the HTTP methods, the resource paths, the integration responses, and all the IAM execution roles. It is honestly brutal. But in a SAM template, you simply add an events property beneath your Lambda function, declare the HTTP path, and hit save. That's it. SAM automatically builds the entire API gateway and wires up all those restrictive IAM permissions for you. Okay, so you wrote the perfect template, but how do you actually get your local code into the AWS cloud quickly and safely? Well, for that, you use the SAM command line interface, commonly known as the SAM CLI. First things first, you run SAM build. The CLI scans your application, installs your specific dependencies, and compiles your deployment packages perfectly. Next, you just run SAM deploy. SAM automatically takes your packaged Lambda code, uploads it to an Amazon S3 bucket, translates your SAM template right back into raw CloudFormation, and executes the stack deployment. You literally never have to manually zip a file or click endlessly through the AWS console again. But listen close, because this is where people mess up big time. They write their code, run SAM deploy, wait 5 whole minutes for the CloudFormation stack to build, realize they made a dumb typo, wait for the stack to roll back, fix the typo, and then deploy all over again. Your iteration cycle becomes agonizingly slow. You are just bleeding time and money at that point. I mean, think about that for a second. Why on earth are you testing in the cloud when you can test right on your laptop? The SAM CLI actually has a built-in local emulator. By running SAM local invoke, SAM spins up a Docker container on your own machine that perfectly mimics the live Amazon Linux Lambda execution environment. You can pass in mock JSON event payloads, debug your API gateway routing locally, and fix your code instantly before you ever push a single file up to AWS. Now, I want you to imagine this scenario. You write a perfect SAM template, you run the deployment, but out of nowhere, the deployment instantly fails with a massive red error stating unrecognized resource type. Heads up, this is a guaranteed trap on the DVA-C02 exam. Why did it fail? Because you forgot to include the transform directive at the very top of the template. Without that exact transform statement, AWS tries to read your custom SAM syntax as standard CloudFormation, gets totally confused by the serverless resource declarations, and violently rejects the entire deployment. Also, you gotta remember that SAM is just CloudFormation under the hood. Anything you can do in standard CloudFormation, like defining outputs, mappings, and parameters, you can do directly inside a SAM template. You can even mix standard AWS resources, like an Amazon SQSQ or a VPC, right next to your serverless functions in the exact same file. It's the whole shebang. So, what does this all mean for you? Let's lock this down with 3 rapid takeaways from this explainer. Number 1. AWS SAM simplifies serverless architecture by using a transform macro to automatically expand a few lines of super clean syntax into massive deployable CloudFormation templates. Number 2. The SAM CLI accelerates developer productivity by allowing you to package dependencies with SAM build, automatically push artifacts to S3, and release infrastructure with SAM deploy. And number 3, you absolutely drastically speed up your iteration cycles by using the SAM CLI to locally debug and invoke your serverless applications using Docker long before ever touching the live AWS cloud. I'll leave you with one final warning. Never, Ever try to build complex, event-driven serverless applications with raw cloud formation? If you aren't using AWS SAM, you are wasting hours writing fragile infrastructure and dragging your entire engineering team's speed down. So ask yourself, are you ready to stop building the hard way and actually let SAM do the heavy lifting for you?
Okay, let's jump right into this explainer. Today, we are looking at AWS safe deployment strategies and risk management. We're going to tackle a very high-stakes reality that every developer faces, which is controlling your production blast radius during an application update. Because, let's be honest, the truth is, a single deployment can literally make or break your application's uptime. So I want to show you exactly how safe deployment strategies work in the real world and exactly how you need to execute them if you're taking the DVA-C02 exam.
I want you to imagine the scenario. It's late, you push what you think is a quick, harmless code update directly to your live servers. But a tiny, unexpected bug in that new code crashes the application. Suddenly, it takes your entire system offline. Users are blocked, errors are spiking, it's a total disaster. Well, good AWS engineers never let this happen. They use safe deployment strategies to strictly control their production blast radius. The core mental model you absolutely must adopt today is simple. Safe deployment strategies strictly reduce risk. You don't just overwrite live code. Instead, you isolate the new version and you transition your traffic safely.
All right, let's look at strategy number 1, the gold standard, blue/green deployments.
So blue/green deployment is a strategy that absolutely minimizes your downtime and your risk. And it does this by running 2 identical production environments. We call them blue and green. Now, here is the key difference. Only one of these environments serves live production traffic at any given time, while the other one is being updated. Once your testing is completely finished, your traffic is simply switched or routed over to that new environment. Think about it like a really busy restaurant. If you want to upgrade, instead of closing down your business to remodel the kitchen, you literally build a brand new, fully functioning kitchen right next door. Your chefs can go in, they can practice in the new kitchen, figure out the quirks, all while the old kitchen is still happily serving your real customers. And once that new kitchen is absolutely perfect, you simply swap the signs on the front doors. Now, to actually build this out in AWS, we rely on a specific set of services. We use things like AWS Elastic Beanstalk, AWS Code Deploy, Amazon Route 53, and Elastic Load Balancing. Each of these services gives us specific ways to implement the routing and the shifting of our traffic back and forth between those 2 environments. Let's actually walk through the exact sequence of how this happens. For example, if we're on an EC2 compute platform, the instances in your deployment group, that's your original environment, are replaced by a completely different set of instances in a replacement environment. First, Code Deploy provisions those new instances, and the absolute latest application revision is installed on them. Then, an optional wait time occurs. This is for activities like deep application testing and system verification. Think about that for a second. You have all the time in the world to run automated tests against these new servers because absolutely 0 real users are touching them yet. Then, once you're confident, instances in that replacement environment are registered with an Elastic Load Balancer, which causes the traffic to be seamlessly rerouted to them. Finally, the instances in your original old environment are deregistered. From there, they can either be terminated to save money, or you can keep them running for a bit just in case.
Okay, moving on to strategy number 2, the pragmatic alternative, canary deployments.
Now, you might be wondering, what if you don't want to double your compute costs by running 2 massive, identical environments at the same time? Or what if you actually want to test the new code on your real users, but you want to do it very, very safely? Well, instead of a massive switch, you use traffic shifting. You might route just 10% of your live traffic over to the new version, while keeping 90% of your users safely on the old version. Think about the power of that. If your new code has a hidden memory leak that didn't show up in testing, only 10% of your users experience a slight slowdown, and you can instantly pull them back to safety. You have completely contained the blast radius of that bug. So tying this back, the absolutely crucial point for the DVA-C02 exam is this. You manage these application environments in individual AWS services by differentiating between your development, your test, and your production stages in API Gateway. You can actually use existing runtime configurations to create dynamic deployments. A great example is using staging variables from API Gateway directly in your Lambda functions. You can also safely test applications using Lambda versions and aliases. It's pretty cool. You simply configure a Lambda alias with routing weights, and that allows you to slowly, carefully shift traffic from the old version over to the new version. All right, strategy 3, and pay close attention here because this is where people mess up. The pitfall, the rolling deployment trap. A lot of teams default to using a rolling deployment instead.
In a rolling deployment, AWS updates your instances in batches. So it takes down maybe 5 instances, upgrades them, puts them back into service, and then moves on to the next 5. Seems logical, right? But if that deployment fails halfway through, you have a massive problem. You now have a split brain environment. Literally, half your users are seeing the old code and half are seeing the new, broken code. And the worst part? Rolling back from that state is a slow, painful, manual process. You are risking serious failure and extended downtime.
Now imagine this. You do the smart thing. You launch a canary deployment. But how does AWS actually know if the new version is failing in the background? That is the ultimate safety net question we have to answer.
The answer is you must instrument your code for observability. Good engineers don't just deploy, they implement an effective logging strategy to record exact application behavior. They add annotations for tracing services, and crucially, they implement code that emits custom metrics. Why? Because if those custom metrics suddenly spike, say error rates shoot through the roof, your pipeline automatically detects it. You can then perform automated application rollbacks by using those existing deployment strategies. Code deploy instantly shifts the load balancer traffic right back to the original instances, and your application effectively self-heals with zero downtime.
All right, let's wrap this up. Let's lock this down. 3 rapid takeaways.
Takeaway number 1. Blue/green deployments minimize your risk by running 2 identical environments, and they use a load balancer to seamlessly reroute traffic only once your testing is totally complete. Takeaway number 2. You configure deployment strategies like canary or rolling deployments to strictly limit exactly how many users are exposed to brand new code at any one time. And takeaway number 3. You absolutely must instrument your code for observability. That way, if an update fails, your pipeline can instantly perform an application rollback using your deployment strategy. I want to leave you with one final crucial warning to think about. Deploying without monitoring is deploying blind. Never, ever assume a deployment succeeded just because the build finished compiling. If you aren't monitoring your traffic shifts and you aren't configuring automatic rollbacks, you are still deploying blind. So keep your blast radius small, instrument your code, and stay safe out there.
Picture this. You push a tiny, one-line bug fix to your AWS environment. It seems completely harmless, right? But 2 minutes later, your API starts throwing HTTP 500 errors, your database connections sever, and suddenly your entire production application flatlines. The panic sets in as customer complaints start rolling in, and your pager is going off uncontrollably.
You didn't just deploy a bug. You deployed a disaster. Why did this happen? Because you built a blazing fast CI/CD pipeline, but you completely forgot to build the brakes. You optimized for speed over operational safety. Section 1. The danger of automation. Why safeguards are critical for the DVA-C02 exam. The core mental model you must adopt right now is this. Automation without safeguards is incredibly dangerous. Let me show you exactly how a single bad deployment destroys an application, and more importantly, how good AWS developers engineer operational safety to stop it in its tracks. Think about it like this. CI/CD is essentially a high-speed freight train. Continuous integration compiles your code, and continuous delivery pushes it out to the server. But if that train is carrying a bomb, and there are absolutely no safety checkpoints along the tracks, that bomb goes straight into your live user environment. Without safeguards, the blast radius is 100% of your users. Everyone is impacted. Now imagine this real-world scenario. You update your AWS Lambda code to expect a brand new JSON payload structure from your front end. You deploy the Lambda function, but you haven't deployed the new front end yet. Or worse, and I'm going to slow down slightly here because this is huge. The new code writes a completely different partition key format to Amazon DynamoDB, but the old front end is still blindly trying to read the old format. You just caused a massive database mismatch issue. Your API is completely broken, and worse, customer data is being corrupted in real time. Just a total nightmare. Section 2. Manual approval gates. The first line of defense. Listen, this is where people mess up. They naturally think automated deployment means absolutely zero human interaction from start to finish. But let me tell you, that is a dangerous assumption. To protect your system, you must implement an approval gate in AWS code pipeline. Here's exactly how it works. Before the code ever touches production, the pipeline physically stops and triggers an Amazon SNS notification. A human QA engineer reviews the staging environment, verifies everything is functioning perfectly, and clicks Approve. Only then does the automated deployment proceed. That one single click, it's literally the difference between a safe, boring release
and an entire weekend of firefighting.
Section 3. Immutable Deployment Strategies. Preventing Live Server Corruption. But what if the bug slips past QA? If you're using an in-place deployment, meaning AWS Code Deploy is installing the new code directly over the top of the old code right on your live servers, you are in massive trouble. If that deployment fails halfway through, your live server is corrupted. Instead, to truly protect your infrastructure, you absolutely must configure deployment strategies like blue/green, canary, or rolling for your application releases. Let's look at how this works on an EC2 compute platform. In a blue/green deployment, the instances and a deployment group are replaced entirely by a different set of instances. Code Deploy provisions a brand new set of EC2 instances. This is your green environment. It safely installs the new code right there. And the beautiful part? The original blue instances are completely untouched. They are still happily serving your users. Once the green environment is fully verified, the instances in that replacement environment are registered with an elastic load balancing load balancer, causing live traffic to be cleanly rerouted over to them.
Think about that for a second. If the new green environment crashes under heavy load, you don't have to panic. You don't have to frantically rewrite code or restore from a backup. You just flip the load balancer straight back to the untouched blue environment. Your recovery time is measured in seconds, not hours.
Section 4. Automated Monitoring and Rollbacks. Building self-healing systems. Now, here's where this gets really interesting. At a certain scale, you don't want to rely on a human to notice the site is down and manually flip that switch. You must rely on sophisticated deployment monitoring and automatic rollbacks.
As an AWS developer, you meticulously instrument your code to emit custom metrics to Amazon CloudWatch. You then configure your pipeline to actively watch a specific CloudWatch alarm during the deployment phase. If your API error rate spikes by even 5%, the CloudWatch alarm trips. The pipeline instantly detects this, halts the deployment, and performs application rollbacks by using those existing deployment strategies we just talked about. The system self-heals before your users even realized there was a glitch in the matrix.
Section 5. Serverless Deployment Traps. Navigating environments without EC2 instances. I need you to really watch out for the serverless deployment traps, especially if you're taking the DVA-C02 exam. Imagine this scenario. You're fully serverless. You don't have traditional EC2 instances or application load balancers to easily shift traffic back and forth. So how do you safely deploy an update to a serverless API without risking taking down a live version? Well, you do this by managing environments in individual AWS services. Specifically, you differentiate between development, test, and production right in API Gateway using stages and Lambda aliases. This segregation is absolutely vital. Without it, a single bad push to a monolithic Lambda function immediately brings down your production API. By separating these stages, you create a hard isolation boundary. Your production users are safely hitting one stable stage, while your developers are freely testing breaking changes in a completely different stage without impacting live traffic.
Here is how you actually execute it. You publish your new Lambda code as a distinct new version. Then, and I'll slow down slightly here because this is key, you use a Lambda alias with a weighted routing configuration to send 90% of your traffic to the old stable version and only 10% to the new version. This is called a canary deployment. If the 10% canary fails, your tiny blast radius means only a small fraction of users are impacted. If it succeeds, you slowly shift the rest of the traffic over time. You combine this by using existing runtime configurations to create dynamic deployments, such as mapping staging variables from API Gateway directly into your Lambda functions. So your production API stage reliably points to the stable alias, and your dev API stage safely points to the latest untested code. Section 6. 3 rapid takeaways. Essential CI/CD operational safety. Let's lock this down before we wrap up this explainer. 3 rapid takeaways you really need to internalize. Number 1, automation without safeguards is extremely dangerous. Always use orchestrated workflows with manual approval gates to prevent unverified code from ever reaching production. Number 2, use immutable deployment strategies like blue/green or canary to drastically reduce your blast radius and enable instant, safe application rollbacks. And number 3, diligently instrument your code to emit custom metrics so your infrastructure can automatically detect deployment failures and self-heal in real time without human intervention. I'll leave you with one final warning. A deployment is not successful just because the code compiled successfully on your machine. A deployment is only successful if you can mathematically prove the live application is healthy and you have a one-click strategy to revert it if it is not.
So take a hard look at your own AWS environment today. If your next deployment fails entirely, are you recovering in 5 seconds or are you recovering in 5 hours?
Mastering AWS CloudWatch, the architect's guide to production logging. Let's dive right in.
Picture this. You wake up at 7 a.m. Your phone is completely flooded with angry emails from customers. Your application crashed at exactly 3 a.m., locking out hundreds of users while you were asleep. Panic sets in. You scramble logging into the AWS console to figure out what went wrong, but your dashboard is completely empty. Here's the hard truth. Your system was warning you. You just weren't looking. Let me show you exactly how to debug these production failures and why logs are your absolute first source of truth when everything goes wrong. Before we dive into the AWS console, we need to understand exactly what we're looking for. When your application is running, it generates 2 distinct types of data: system logs and application logs. System logs are the underlying server telling you what it's doing. Things like, I just ran out of memory, or my CPU is maxed out. Application logs, on the other hand, are your custom code telling you what it's doing, like, I successfully connected to the database, or, more importantly, user authentication failed. You absolutely need both to survive an outage. To capture all this crucial data in AWS, you use Amazon CloudWatch Logs. Simply put, CloudWatch Logs is a centralized repository that allows you to monitor, store, and access log files from your entire architecture in a highly scalable way. But AWS doesn't just take all of your text and throw it into one giant, unorganized bucket. That'd be a nightmare to search. Instead, it uses a very specific, strict architecture to keep you organized. Think about it like this. A log group is like a massive filing cabinet dedicated entirely to one specific application. If you have a billing app, it gets its own filing cabinet. Inside that massive filing cabinet, you have hundreds of individual folders. Those folders are your log streams. A log stream represents a sequence of log events from one specific source, like a single Amazon EC2 instance or one specific container running your code. It keeps the chaos organized. So how does the data actually get into those individual folders? Well, if you're using a managed service like AWS Lambda, the logging is beautifully automatic. AWS automatically creates a log group for your Lambda function and pushes all of your standard output and error messages directly into a log stream for you. But this is where people mess up. They launch an Amazon EC2 instance, they install their web application, and they just assume AWS is automatically capturing all their application logs. It's not. By default, CloudWatch has absolutely no visibility into the hard drive of an EC2 instance. To get those logs out, you must manually install and configure the CloudWatch agent on your server to actively push those log files into CloudWatch. Now here's where this gets really interesting. Just getting raw text into CloudWatch isn't enough to save you at 3 a.m. If your application is generating unstructured logs, meaning just massive raw sentences of text, you're literally going to spend hours scrolling through lines of code trying to find a single error. To engineer this correctly for production, you must use structured logging. You do this by formatting your log outputs as JSON. When your logs are structured as JSON key value pairs, you unlock a massive feature called CloudWatch Logs Insights. Insights is an interactive query engine. It allows you to run fast SQL-like queries across millions of log lines instantly. Instead of reading, you write a single query that says, show me every log where the status is 500 and the latency is over 2 seconds, and it will hand you the exact root cause of your 3 a.m. outage in milliseconds. Now, imagine this scenario. You don't want to wait until 7 a.m. to find out your app crashed. You don't want your customers telling you the system is down. You want AWS to catch the failure the exact second it happens. To do this proactively, you use a metric filter. A metric filter constantly and automatically scans your incoming log streams, evaluating the incoming text for specific terms, phrases, or values. For example, you tell it to look for the word exception. Every single time that word hits the log stream, the filter increments a custom CloudWatch metric. You then set a threshold. If that metric hits, say, 10 exceptions in 1 minute, it immediately triggers a CloudWatch alarm, waking you up at 3:01 a.m. so you can fix the issue before the users even notice. But what if you need to react even faster? If you need near real-time processing of your logs, you use a subscription filter. Instead of just counting words, a subscription filter takes your live, incoming log events and streams them directly into an Amazon Kinesis data stream or triggers an AWS Lambda function for instant, custom processing. This is exactly how you build truly self-healing architectures. Now, whether you're building this in the real world or studying for your AWS certification, watch out for these 2 massive exam traps on the DVA-C02. Let's dive into the first one. Trap number 1. Log retention. By default, Amazon CloudWatch Logs retains your data indefinitely. Let me repeat that. It keeps it forever. If you have a high-traffic production application generating gigabytes or terabytes of logs every single day, and you leave the default settings on, your AWS bill will quietly explode. It's a massive pain point. To prevent this, you must explicitly configure a log retention policy on your log group, telling AWS to automatically delete or archive those older logs after a specific time frame, ranging anywhere from 1 day up to 10 years. Trap number 2, the missing logs mystery. Imagine you deploy a brand new Lambda function. It fails. You open up CloudWatch to read the error, but the log group does not exist. There are 0 logs. Where did they go? Why does this happen? Well, because AWS is completely locked down by default. Your Lambda function's execution role must have explicit IAM permissions attached to it, allowing it to write to CloudWatch. Specifically, it needs the logs create log group and logs put log events permissions. If you forget to give your compute resource explicit permission to write logs, AWS will silently drop every single error message your code generates. No warnings, no alerts. You will be completely blind during an outage. Let's lock this down. Here are your 3 rapid takeaways to master CloudWatch logs. 1. Logs are your absolute first source of truth during an outage. Use log groups to organize your applications and log streams to track individual sources. 2. You must proactively manage your logs by installing the CloudWatch agent on EC2 instances, setting strict retention policies to avoid massive AWS bills, and ensuring your Lambda execution roles actually have the IAM permissions to write logs. 3. Implement structured JSON logging so you can instantly troubleshoot complex issues using CloudWatch Logs insights, and use metric filters to trigger alarms the very moment a specific error is written to the logs. I'll leave you with one final warning. If you aren't logging your application's state correctly, you aren't actually running a production system. You're just waiting for a disaster you can't explain. So, what invisible failures are hiding in your architecture right now? All right, let's dive right into it. How exactly did Netflix know their servers were failing before a single customer even complained? Or think about this. How did they know a database node was locking up before a single person's movie even started buffering? Well, it's because they didn't just sit around waiting for humans to notice the problem. No, they built a system that actively monitors its own heartbeat, right? It detects the exact moment an organ starts completely failing, and it literally performs surgery on itself while the engineers are fast asleep. So let's look at exactly how AWS detects these outages before humans ever do, and how you can engineer this kind of self-healing automation for the DVA-C02 exam. To understand how AWS actually knows your server is dying, you really have to understand Amazon CloudWatch. You can think of CloudWatch as the central nervous system of your entire AWS architecture. It's this monitoring and observability service that continuously collects and tracks data across all your applications. In the most fundamental building block here, it's called a metric. A metric is quite simply a time-ordered set of data points. Think of it almost like taking a server's pulse. Every few minutes, your Amazon EC2 instances are automatically sending metrics back to CloudWatch, things like CPU utilization, disk reads, and network traffic going out. But if you've got 1,000 servers running, how do you find the exact pulse of just one? Well, CloudWatch organizes this massive ocean of data using what we call namespaces and dimensions. A namespace is basically your top-level container, something like AWS/EC2 or AWS/DynamoDB. Then you have a dimension, which is a specific name-value pair that uniquely identifies the exact resource inside that container. For example, instance ID equals I-123456789, and this is exactly how you filter out all the noise. You're telling CloudWatch exactly which server it needs to look at. Now, here's where this gets really interesting. A metric by itself is completely useless. I mean, it is just a number sitting on a customizable CloudWatch dashboard. If a server's CPU spikes to 100%, sure, the dashboard is going to show a big red line. But if nobody is actually looking at the screen, your app still crashes. So to actually protect your production environment, you absolutely must build CloudWatch alarms. An alarm actively watches a single metric over a specified time period. You go in and set a strict threshold. For example, you might tell the alarm to trigger if the CPU utilization goes over 80%. But listen, this is where people mess up, and it is a massive trap on the exam. Imagine a developer sets the alarm, a server experiences a tiny 1-second CPU spike, the alarm instantly triggers, and it completely tears down a perfectly healthy server. Why did that happen? Because they didn't understand operational behavior. CloudWatch alarms do not invoke actions simply because they hit a state for a split second. No, alarms invoke actions for sustained state changes only. You have to configure the alarm to evaluate the metric over a specific number of periods, like exceeding 80% for 3 consecutive 5-minute periods. You only want the alarm to take action when the server is actually dying, right? Not when it just sneezed.
So when the alarm finally does trip, it initiates some automated actions. First, it fires off a message to an Amazon SNS topic. SNS instantly pushes a text message or an email directly to your on-call engineer's phone. Second, the alarm triggers an Amazon EC2 autoscaling policy. Autoscaling immediately steps in, permanently terminates that dying, unresponsive server, and spins up a brand new, perfectly healthy instance to replace it.
I want you to think about that for a second. You didn't write a single line of recovery code. You didn't manually log into a server to reboot a service. You literally just mathematically defined what healthy looks like, and the AWS ecosystem automatically healed your architecture the very second it drifted from that baseline. Now, imagine this scenario. You deploy a highly complex application. Out of nowhere, users start complaining that their shopping carts are failing to check out. You panic. You check CloudWatch, but the EC2 CPU is fine. The network is fine. The database is perfectly fine. All your standard AWS metrics are telling you that your system is running perfectly.
But your system is actually burning to the ground.
Why does this happen? Well, because standard AWS metrics only monitor the underlying hardware. AWS has absolutely no idea how your specific business logic is actually performing. It doesn't know how many failed logins you have or how many shopping carts are crashing. So to fix this, as an AWS developer, you have to build custom metrics. You write code inside your application using the AWS SDK to make a put metric data API call directly to CloudWatch. That way, every single time a checkout fails, your code publishes a custom data point straight to CloudWatch. But there is a catch here. If you're running, say, a massive flash sale and thousands of transactions are happening every single second, the default 1-minute or 5-minute metric resolution is just entirely too slow. I mean, by the time 5 minutes passes, you've lost thousands of dollars. So for critical, real-time production monitoring, you absolutely must configure high-resolution metrics. This feature allows you to publish and track custom metrics down to a 1-second granularity, meaning if that shopping cart fails, you know about it in exactly 1 second.
You do need to watch out for the data retention limits, though. Your standard 1-minute metrics are stored for 15 days, but those incredibly dense 1-second high-resolution metrics, CloudWatch only retains those for exactly 3 hours before they expire. If you don't act fast, that granular data is gone forever. And just as a quick side note to remember, you cannot manually delete a metric in CloudWatch. You just have to wait up to 15 months for it to automatically expire on its own.
All right, let's lock this down. 3 rapid takeaways for you. Number 1, CloudWatch organizes monitoring data using namespaces and dimensions, which allows you to isolate and track the exact performance metrics of individual AWS resources. Number 2, CloudWatch alarms evaluates sustained state changes over time to automatically trigger Amazon SNS alerts and auto-scaling policies to self-heal your infrastructure. And number 3, you must use to put metric data API to publish custom metrics to monitor your unique application logic, and use high-resolution metrics for 1-second visibility during those critical events. I'll leave you with one final warning. Never, ever build an alarm that only sends an email. If your only response to a dying server is to wake up a human and ask them to fix it, well, you have fundamentally failed at cloud architecture. Automate the recovery. So I have to ask, is your cloud architecture currently working for you, or are you working for it?
Picture this scenario. You suddenly get a critical alert. Your user checkout process is taking 5 full seconds. Now, you know as well as I do, 5 seconds in e-commerce, that is an absolute eternity. It is a guaranteed way to lose customers and, more importantly, lose money. Your standard logs are pointing fingers all over the place, but honestly, they are effectively lying to you about where the actual problem is. Well, let's dive into this explainer and solve the mystery of tracing the invisible.
So here is the immediate pain point. You frantically check your Amazon API gateway metrics and, yep, the latency is definitely 5 seconds. You go check your AWS Lambda execution time, and it is also sitting right at exactly 5 seconds. Now, if you stop your investigation right here, you are going to spend hours rewriting your Lambda code, desperately trying to optimize a function that is actually running perfectly fine.
So, why is the API choking? Think about that for a second. The API wasn't actually slow. One hidden dependency was.
Because let's face it, in a modern distributed microservices architecture, your code rarely works in isolation. Rewriting that Lambda code is a massive mistake, because the bottleneck? It's somewhere else entirely. Let's walk through this workflow and see how it all connects. Your Lambda function isn't just sitting there computing math in a vacuum, right? It's talking to other services. First, a request hits the API gateway, which triggers your Lambda. Then, Lambda talks to Amazon DynamoDB. It makes an HTTP call out to a third-party payment provider like Stripe, and finally, it drops a message into Amazon SQS. If just one of those downstream services chokes, your entire application grinds to a halt. You simply cannot solve distributed latency by staring at a single server log.
What you actually need is end-to-end visibility. You need AWS X-Ray. To do this, X-Ray relies on one absolutely critical component, and that's the Trace ID. AWS X-Ray is a distributed tracing service that literally follows a single user request from the exact millisecond it hits your front door all the way through every single backend service. It manages this by injecting a unique HTTP header, the Trace ID, right into the request. You can think of it exactly like a digital tracking device slapped onto a package.
As that request moves from your API gateway over to Lambda and down to your database, every single service records what it did, how long it took, and hands that data right back to X-Ray. X-Ray then takes all of those scattered individual data points and stitches them together into two incredibly powerful tools, the trace map and the trace details. You literally get a live visual web of your entire architecture. You can watch the requests hop from node to node with the exact latency numbers and error rates hovering right there over the connection lines. It's pretty amazing.
But how does X-Ray actually break down the time spent inside your compute resources? Well, it uses two main concepts. The first is the segment. Think of a segment as the overarching record of the compute resource itself. When API Gateway receives the request, it creates a segment. When Lambda takes over, it creates its own segment. The segment essentially raises its hand and says, "Hi, I am the Lambda function, and I ran for 5 seconds." But a segment alone doesn't tell you why it took 5 seconds.
For that deeper why, you need the subsegment. Subsegments give you the granular, line-by-line timing details of exactly what your application code was actually doing under the hood. When your Python code pauses to make a database query, the AWS X-Ray SDK wraps that specific action in a subsegment, peeling back the layers to reveal the true hidden timing details beneath the surface.
Now look at how the trace details expose the actual truth. You open up the X-Ray console for that failing 5-second checkout. The main Lambda segment? Sure, it says 5 seconds, but look right underneath it at the breakdown. The DynamoDB subsegment? Just 20 milliseconds. The SQS subsegment? A mere 15 milliseconds. But that external HTTP subsegment calling the Stripe API? 4.9 seconds. Boom. You have instantly isolated the root cause. So, the absolutely crucial point here is that you do not need to rewrite your database queries. You don't need to touch your Lambda execution logic at all. The actual fix required for this system is to just implement a strict timeout or a circuit breaker on your third-party API calls. By seeing the invisible, you just saved yourself hours and hours of completely unnecessary database optimization. Now here's where this gets even more interesting. What if the external API is fast, the database is lightning fast, but the total Lambda duration is still inexplicably slow? Well, X-Ray actually exposes the exact initialization time of your Lambda execution environment. It physically draws a line right on your trace, visually separating the cold start latency from your actual code execution time. With this, you can definitively prove if your API is just suffering from cold starts rather than bad code. And on top of that, X-Ray is incredibly smart about how it draws your architecture. Some services, like DynamoDB for instance, don't natively send their own segments to X-Ray. But because your Lambda code generated a subsegment when it made the database call, X-Ray uses that context to automatically draw what's called an inference segment on your map. It exposes that downstream dependency even if the target service doesn't actively support tracing.
All right, part 1, the trap, finding the exact request.
Now, I really need you to slow down and listen closely to this next part. Out of millions of daily requests, how do you find the one single trace for the specific customer who complained? This is where people mess up, and it is a massive guaranteed trap, especially if you're studying for the AWS DVA-C02 exam. You naturally want to search your traces by a specific user ID or order ID, right? Well, X-Ray allows you to inject this custom business data into your segments, and you have two options to do it: annotations and metadata. A developer will very often inject the order ID as metadata. They go to the console, they search for that order ID, and they get absolutely zero results. Why? Because metadata is completely unindexed. It is literally just extra context stored in the payload. You cannot search it.
To implement this correctly, you must use annotations. Annotations are explicitly indexed by AWS. If you attach that order ID as an annotation instead, you can instantly filter millions of traces to find the exact request that failed for that exact customer during a massive production outage. It is a total game changer.
Moving on to part 2, the performance trap, catastrophic compute overhead. There is one more major pitfall to watch out for here. If you have a high-throughput API handling, say 10,000 requests a second, tracing every single one of those requests is going to result in crushing compute overhead and a frankly catastrophic AWS bill. You don't want that. Instead, you need to configure X-Ray sampling rules. You basically tell X-Ray to record, for example, just the first request every single second, and then only 5% of any additional requests after that. This kind of smart sampling gives you a statistically significant view of your application's health, saving you serious money without crushing your API's performance.
All right, let's lock this down before we finish up today. 3 rapid takeaways to remember. Number 1, AWS X-Ray tracks requests visually across your distributed systems using a unique trace ID. Number 2, segments represent the overall compute resource, while subsegments give you the granular timing to expose those hidden downstream dependencies. And number 3, you absolutely must use annotations, not metadata, to index and search your traces for custom business data. I want to leave you with this final thought. It's time to stop guessing where your code is failing based on generic server logs. If you aren't tracing your requests end-to-end, you aren't engineering a system, you are just blindly hoping the network behaves. Think about that for a second. If your system went down right now, would your standard logs tell you the truth, or are you just relying on hope? Implement X-Ray, take full control of your architecture, and stop guessing.
Welcome to this explainer. You know, we have all been there. You write this beautiful, perfectly tested Python code. You run it on your local machine, and it works flawlessly. Every test passes. But the exact moment you deploy it to AWS and real users start hitting your API in production, boom, you get hit with a massive spike of HTTP 500 errors. You log into the AWS console in a total panic. You look at your metrics, and your Lambda function just keeps timing out. The frustration there is absolutely real, especially because when downtime spikes, money is literally being lost. So, this brings us to the million-dollar question. Why does perfect local code fail in Lambda? The hard truth you need to hear is that serverless compute is not a standard web server. You absolutely cannot treat it like a traditional, always-on machine. Failure happens when you don't understand how Lambda actually executes your code beneath the surface.
Okay, let's lay out our roadmap for today's briefing. We are going to show you exactly why Lambda fails in production, and more importantly, how to engineer your way right out of it. We are covering number 1, the local versus prod trap. Number 2, the Lambda execution lifecycle. Number 3, memory versus timeouts. Number 4, the VPC networking trap. And finally, number 5, production debugging tools.
Let's jump right into section 1, the local versus prod trap. Moving on to section 2, the Lambda execution lifecycle. Let's look at how Lambda actually boots up.
So unlike your laptop, which is this warm, constantly running machine with background processes ready to go, Lambda is a cold, ephemeral reality. It spins up, it does its job, and then it vanishes. To stop these timeouts, we have to understand how a serverless function boots up from absolutely nothing to handle a user request. There are 3 distinct phases here. First, we have the init phase. This is where Lambda prepares the environment. It downloads your code, starts the runtime, and runs any initialization code that sits outside of your main handler. This is what we call the infamous cold start. Next comes the invoke phase, which is where your actual handler code finally runs. And lastly, the shutdown phase, where the environment is totally cleaned up.
Now here is the fatal architectural trap so many developers fall right into. If you import a massive dependency, like a heavy machine learning library, inside your handler function, you are forcing Lambda to load that heavy library from scratch on every single user request. It eats up your precious execution time, and your function times out before it even gets a chance to process the data. Think about that for a second. You absolutely must initialize heavy dependencies globally outside the handler. By doing it outside, they are only loaded exactly one time during that initial init phase. Which brings us to Section 3, Memory versus Timeouts. Let's talk about fixing these errors.
Let's shift our focus to timeout limits, and honestly, the single most costly mistake you can make. By default, a Lambda function times out after just 3 seconds. Now you can raise this limit all the way up to a maximum of 15 minutes. And this is exactly where people mess up. They see a timeout error in their logs, they panic, and they immediately crank the timeout limit straight to the 15-minute maximum. That is a terrible idea. If your code is hanging, you are literally just paying AWS to wait 15 minutes for your broken code to fail.
Instead of tweaking the clock, you need to look at memory. In AWS Lambda, CPU power and network bandwidth are strictly tied to the amount of memory you allocate. If your function is doing heavy data processing and it times out, allocating more memory literally gives it a faster processor. For example, a function running at 128 megabytes might completely choke, exhaust its compute power, and time out after 10 seconds. But that exact same function, if given 1024 megabytes, gets a massive CPU boost and slices through the exact same data in just 200 milliseconds.
Let's look at Section 4, the VPC networking trap. This is the ultimate exam scenario. This specific trap happens in production all the time. What if you gave your function a massive 10 gigabytes of memory, a full 15-minute timeout, and it still hangs and dies every single time? Well, it's usually because of this. Imagine your Lambda function needs to talk to a private Amazon RDS database. So, naturally, you attach the function to your private VPC subnet. But later in your code, that same function tries to make an HTTP request to a public API, like Stripe, or even a public AWS service like S3. The request just hangs until it dies. Why does it hang? Because of this number right here. 0. 0 is the exact amount of default internet access a Lambda function has the precise second you attach it to a VPC. It completely loses its default public routing. It cannot reach the internet at all unless you explicitly deploy a NAT gateway in a public subnet and configure your routing tables. Without that explicit network path, your Lambda function just sits there in the dark and it times out. Moving to Section 5, Production Debugging Tools. It is time to stop guessing in production.
Let's transition away from the underlying causes and look at the exact tools you need to stop guessing. When a function crashes or hard resets during that invoke phase, you must rely on 3 specific tools. Please do not guess. You need to use Amazon CloudWatch logs, AWS X-Ray Active Tracing, and a dead letter queue.
First up, dive into CloudWatch logs. Look specifically for the report line at the very bottom of the execution block. In the modern logging format, AWS actually explicitly tells you what broke. You're going to see either status, timeout, or error type runtime exit error. Finding this explicit line instantly determines if you hit a hard timeout wall or if your code simply threw an unhandled exception that crashed the whole environment. But what if the timeout isn't actually your Lambda code's fault? What if your code is just waiting on an incredibly slow downstream database query? This is where AWS X-Ray Active Tracing comes in. X-Ray visually isolates these downstream delays. It breaks your entire request into segments, so it can definitively prove that your Lambda code ran perfectly, but the DynamoDB subsegment took 2.9 seconds, which caused your 3-second Lambda hit a brick wall. You isolate the bottleneck instantly. Finally, if your function is processing events asynchronously, like reading messages off an SQS queue, you absolutely cannot let a timeout silently destroy your data. You must configure a dead letter queue, or a DLQ. When Lambda exhausts all of its retries, the DLQ automatically routes that failed event payload safely aside. This allows you to go in and analyze exactly what corrupted data broke your code without losing that data forever.
All right, let's lock this all down. Here are 3 rapid takeaways to engineer your way out of timeouts once and for all. Number 1, initialize your heavy dependencies globally, outside your handler, to dramatically reduce those cold starts. Number 2, scale your memory to increase CPU power instead of just blindly maxing out the timeout clock. And number 3, remember that attaching to a VPC completely strips your public internet access. You must use a NAT gateway or your external API calls will permanently hang.
I want to leave you with this final provocative architectural warning here on our last slide. A timeout is a symptom, not a root cause. If you just keep raising that timeout limit without tracing the exact bottleneck using X-ray and proper architecture, you aren't actually engineering a solution. You are just inflating your AWS bill. Take these tools, apply them directly to your infrastructure, and stop paying AWS to wait.
Welcome to the Idempotency Blueprint. Today, we're diving into this explainer to tackle a massive challenge that literally every cloud engineer faces, especially if you're gearing up for that AWS developer exam. We're talking about retries, network failures, and a really crucial architectural concept called idempotency. If you've ever built an API or worked with microservices, you already know things don't always go according to plan. But what if the problem isn't that your code failed, but rather that it worked a little too well?
Your system didn't fail. It succeeded twice. Imagine this absolute nightmare scenario. You just built this blazing fast checkout API. A customer comes to your site, they click buy, the little spinner spins, and they get a nice green success message. But a minute later, their phone buzzes. 2 gank alerts. You just charged them twice for the exact same order. So how in the world does one single click turn into 2 separate credit card charges? Well, it happens because of a fundamental misunderstanding of how modern infrastructure handles failures.
The root of this whole problem comes down to what we call transient failures. Think about it like this. The internet is just incredibly unstable. Packets drop all the time, database connections randomly time out. These are transient failures. They're temporary network glitches that usually fix themselves in just a few milliseconds. And because these glitches are so unbelievably common, AWS SDKs and modern frameworks are designed to not just give up when an API request fails. Instead, they automatically retry the request. Now, usually this is a total lifesaver, but sometimes it's a disaster.
Let's walk through exactly how this sequence plays out and see why your absolutely perfect infrastructure can actually betray you. Step 1. The client sends the charge request. Step 2. That request hits your AWS Lambda function, which then talks to the payment gateway. Step 3. The payment actually succeeds, the money moves. But then step 4. On the way back, a network router blips, and the success response never reaches the client. The client is just left hanging, assuming the whole thing failed. So what does it do in step 5? It retries. It fires off the exact same request again. Your Lambda function blindly accepts it, hits that payment gateway again, and charges that poor customer a second time.
Think about that for a second. Your infrastructure worked perfectly. The retry mechanism did exactly what it was programmed to do, and you still lost a customer's trust forever simply because you didn't protect your code against retries. And this gets even more dangerous when you introduce a distributed message queue like Amazon SQS. Standard SQS provides what's known as at least once delivery. It absolutely guarantees your message will be delivered, but it explicitly warns you that occasional duplicates are just going to happen. Or think about an SQS to Lambda integration. Your Lambda function picks up a message to process an order. It processes the order perfectly, but right before Lambda can delete that message from the queue, the function times out. So the message becomes visible in the queue all over again. Another Lambda function instantly picks it up and processes the exact same order a second time. Normal, everyday distributed system behaviors are creating duplicate transactions right under your nose. So the really crucial question here is, how do we stop this? How do we prevent our code from duplicating critical transactions when AWS forces a retry? Well, the architectural cure is called idempotency. It's actually a mathematical concept, and it simply means that an operation produces the exact same result whether you run it once or 1,000 times. If you retry a failed payment, it shouldn't charge the card twice. It should just gracefully return the original success message. Let's compare the two approaches. In a non-idempotent setup, the Lambda blindly accepts the retry and slams the payment gateway again. Bad news. But in an idempotent solution, you force the client to generate a unique idempotency key or client token when they make the very first request. Now, when your Lambda function receives that request, it immediately checks an Amazon DynamoDB table. It asks, hey, have I seen this exact token before? If the answer is no, it processes the payment and saves the token to the database. But if the answer is yes, it instantly stops and says, already done, without ever touching the payment gateway again. You have mathematically eliminated double charges. Now, what's really interesting about this next part is how the scale of the problem shifts. We've solved the single user error, but what happens when a backend database actually goes down and every single API request starts failing at the exact same time? You get what's called a retry storm. All your clients instantly retry. Then they retry again. Thousands of requests hit your system at the exact same millisecond. Because of that automated retry logic, you accidentally create a massive denial of service attack against your own application. You are literally DDoSing yourself. This is an immense architectural threat that can completely crush your backend servers right when they're trying to recover. To fix this, you absolutely must implement exponential backoff and jitter. Notice how the delay time shifts here. Exponential backoff means the client waits longer between every single failed retry attempt. 1 second, then 2 seconds, then 4, then 8. And jitter? That's the secret sauce. It adds randomness to that delay time. By doing this, you ensure that 10,000 clients don't all retry at the exact same millisecond. You mathematically spread the load out over time, which gives your struggling database the crucial breathing room it desperately needs to recover. Now, pay very close attention here because this is where people mess up. This is a massive trap, especially if you're taking the AWS exam, the infinite loop trap. Developers will often set their Lambda functions to just retry indefinitely. But what if an SQS message contains a bad payload, like a poisoned pill? Lambda will pick it up, crash because of the bad data, and return the message right back to the queue. Then it picks it up again, crashes again, and retries. Forever. You end up literally paying AWS for an endless loop of failure. You have to break that loop. Instead of letting an infinite retry loop eat your entire AWS budget, you use a dead letter queue, or DLQ. You basically configure AWS and say, hey, if this message fails 3 times, stop retrying. Move it over to this separate SQS queue. This DLQ acts as a vital backup system. It immediately isolates the bad data, so your system can keep happily processing healthy orders, and your engineering team can safely go debug that poisoned message later. All right, let's lock this down. Here are the 3 rapid takeaways you really need to master this topic. 1. Network requests will fail. You must design your applications fully expecting automatic retries from SDKs and at least once delivery from services like SQS. 2. Implement idempotency using unique client tokens to ensure duplicate requests never result in duplicated business transactions. And 3. Always use exponential backoff with jitter to prevent retry storms and configure dead letter queues to safely capture poisoned messages. I'll leave you with this final provocative thought. Stop trusting the network. If your application code assumes a request will only ever arrive exactly once, you are operating on borrowed time. You are literally one network clip away from a massive production disaster. Build for failure, build for retries, and design your systems to be mathematically resilient. Welcome to This Explainer. Let's just dive right into this with a pretty scary truth. Your AWS bill exploded before your app crashed. Back in the old days of on-premise data centers, if you wrote highly inefficient code, the CPU would just max out, your application would slow to a crawl, and eventually it would crash. But in the cloud, performance optimization is resource optimization. AWS is entirely elastic. It's designed to scale automatically to meet demand. So if your code is terribly inefficient, AWS doesn't automatically throttle it, it just throws more and more hardware at it to keep it running fast. And that is exactly why your application becomes incredibly expensive before it ever becomes slow. Let me show you how to actually optimize your AWS applications for both speed and cost so you don't accidentally bankrupt your company. Let's start with AWS Lambda and look at memory and scaling traps. The most critical execution behavior you absolutely must understand is how Lambda scaling actually works. When you configure a Lambda function, you really only allocate one primary resource, and that's memory. So a developer wants to save money, right? They set the memory to the absolute minimum, 128 megabytes. But in Lambda, CPU power and network bandwidth are strictly tied to the amount of memory you allocate. And this is where people mess up. Think about it like this. You have a compute-heavy task. At 128 megabytes, the function lacks CPU power and it takes 10 full seconds to execute. Because you pay for the exact execution duration, you just paid for 10 seconds of compute time. Now, if you bump that memory up to 1024 megabytes, it gets a massive CPU upgrade and finishes the exact same task in just 200 milliseconds. Even though the higher memory tier costs more per millisecond, the total execution duration is so much faster that your overall build drops dramatically. It honestly feels like AWS math magic, but really it's just efficient compute. You must profile your application performance to determine the exact minimum memory and compute power required to find that perfect cost-to-speed ratio. Now imagine this. Your Lambda function needs to talk to a relational database. You write your code, and you initialize the AWS SDK and the database connection directly inside the main handler function. Every single time a user hits your API, Lambda creates a brand new TCP connection to the database, executes the query, and then tears the connection down. That network handshake alone takes 200 milliseconds. If your app gets 10 million requests a month, you are paying for 2 million seconds of pure networking overhead. To fix this, you absolutely must initialize your heavy dependencies and database connections globally, outside the handler function. When Lambda spins up an execution environment during the init phase, it establishes the database connection exactly once. Then, during the invoke phase, every subsequent request reuses that exact same connection. Your API latency drops, and your execution costs plummet.
But what happens when thousands of users hit your API at once, and Lambda has to quickly spin up brand new execution environments? Well, you get hit with cold starts, which add massive latency delays to your application. To prevent these cold starts, developers enable provisioned concurrency, which keeps execution environments pre-warmed and ready to respond instantly. Now here's where this gets really dangerous. Provisioned concurrency is not free. If you blindly provision 100 concurrent environments, but your app only actually needs 10, you are paying a heavy hourly rate for 90 idle servers doing absolutely nothing. You must actively monitor your concurrency metrics in Amazon CloudWatch and right-size your infrastructure. Your compute is now optimized, but your database is secretly draining your budget. Let's look at Amazon DynamoDB. DynamoDB charges you based on read capacity units, or RCUs, in write capacity units, or WCUs. Let's say a developer needs to find all recent orders placed by a specific user, so they write a scan operation. A scan reads every single item in the entire table before filtering out the results. It's literally like reading a 500-page book cover to cover just to find one person's name. If your table is 50 gigabytes, a single API request just consumed thousands of RCUs to find one single order. Because you have DynamoDB autoscaling turned on, AWS instantly scales up your provision capacity to handle this massive read load. Your application stays blazing fast, but your database bill just hit 5 figures. On the DVA-C02 exam and in real-world production, you must always avoid scans. You must use a query operation. A query uses the primary key to jump directly to the exact item, consuming just a fraction of a single RCU. Think about that for a second. You just turned a $1,000 database operation into a fraction of a penny, purely through better operational design. And if your API still demands extreme read throughput, you don't just endlessly increase your DynamoDB capacity, you implement application-level caching. By placing DynamoDB Accelerator, or DAX, in front of your database, you serve repeated read requests directly from memory in microseconds. Caching is absolutely the ultimate optimization strategy because it entirely removes the operational load from your primary database, drastically reducing your RCUs and API latency. Let's lock this down. Here are 3 rapid takeaways for you. Number 1. In AWS Lambda, CPU and network performance scale directly with memory. This means giving a function more memory often makes it execute faster and cost less overall. Moving to number 2. Always initialize SDK client and database connections globally, outside the Lambda handler, to reuse connections across invocations and eliminate networking overhead entirely. And finally, number 3. Never use a DynamoDB scan operation on a large table. Always use a query or implement in-memory caching with DAX to protect your read capacity units from exploding. I want to leave you with one final warning. You cannot optimize what you cannot see. If you aren't actively monitoring your execution duration and autoscaling events in CloudWatch, your first warning sign won't be a slow application. It will be a massive invoice from AWS. So take a look at your architecture today. What hidden elastic traps are secretly inflating your cloud bill right now?